Good morning. I have a herd of elephants on my roof. I don't know what they're doing up there. Sounds like they're running from lions. Sympathetic. Not even I can sleep through. Oh, yeah, definitely. Yep, insurance got it. Thank goodness. Yeah, that hailstorm, man. Whew. It kicked our patella. Literal holes in our roof. Not just dents, but exposure of the wood below. It was pretty brutal. Pretty brutal. Okay, let's see. What did we do yesterday that you guys definitely need to know for the test? We went through a flow chart. Let me see if I can get this thing up and running without blowing up my computer. Looking good so far. All right, no explosions. We're good. Let me get this open. Share this. So the synthesis of thyroid hormone will definitely be on the test. No if and or buts. Now, it's not like I'm typically going to have you draw this entire thing out on the exam, although sometimes I can. Often I'll say, draw this flow chart and then tell me what blah, 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 blah would do. So for instance, what would happen if you had a patient that did not have, maybe they had a mutation and they were unable to produce thyroglobulin? What's going to happen to T3, T4 production? Increase, decrease, no change. Not too, excuse me, sorry. So they're not able to produce thyroglobulin right here. So this part of the story doesn't exist. Therefore, there's no exocytosis of thyroglobulin. So you can build up as much iodine as you want inside of the colloid. If it cannot combine with thyroglobulin, we no longer have MIT, DIT. We don't have the proper combination to T3, T4. So what would happen to the production of T3, T4? It would decrease. Does that make sense to everybody? We're starting right off the bat. What if we didn't have the proper cell signaling process that drove exocytosis? What if it didn't stop? But what if the exocytosis of thyroglobulin started to decrease? What would happen to T3, T4? Release, production? What would our patient end up looking like? Would they be hypothyroid, hyperthyroid, normal thyroid, so hyper, hypo, or normo? You see how powerful writing things out in a flow chart is. It really helps you understand not just normal physiology, but all pathos, all possible pathos that follow this flow chart. So much can go wrong. Now you guys know why there are so many thyroid issues, for instance. So many potential types of diseases. You can't just say that a patient's hypothyroid and always treat them exactly the same because you don't know what the root of the cause is. What if somebody just doesn't consume iodine? Well, we're going to treat them different. We're going to treat somebody with a mutation, thyroglobulin. Does that make sense? Cool. So those are the sorts of things that I would have you do. I'd make you draw the flow chart out. You don't have to do it in this diagrammatic form. You can just do a flow chart. But then I'd make you think through a problem. I'd say, what would happen to a patient if this part of the flow chart was broken? Would it increase? Would it decrease? So forth, so on. So for instance, let's not forget that this synthesis process, this endocytotic process, this exocytotic process, this is all driven by TSH. So now if I start to mess with TSH, thyroid stimulating hormone, now if I decrease TSH, I have less thyroglobulin synthesis, I have less production of T3, T4, I have less endocytosis and, lysozyme function. release of T3, T4. All right, let's go up to the whole liver idea. The liver produces 90% of your plasma proteins. A lot of those proteins act as carrier proteins. The carrier protein for T3, T4 was TBG, thyroxine binding globulin. Thyroxine is the other word for T3, T4. So just like we talked about yesterday, what would happen if there was not enough TBG? If TBG was decreased for whatever reason, what would this patient end up looking like? Hypo, hyper, or normo? Yeah, even though they're producing plenty of T3, T4 potentially, they're not transporting it to where it needs to go, and they will end up having hypothyroid-like symptoms. Cool, you guys are getting this, right? Not too crazy. It all works. It all will make sense. It just takes practice. It just takes practice. Redundant. So, yeah, you got. Therefore, due to homeostasis and negative feedback loops, the brain's going to start to amp up its production of TRH and TSH. Make sense? To truly understand this, we're going to take about 5 more minutes, maybe a little bit more, but hopefully not too much more than that. And I want to actually talk about some forms of potential, well, it doesn't really matter which hormone we talk about, whether we talk about cortisol or thyroid hormone or growth hormone, these guys all act the exact same. So let's look at one loop, and then we're going to start talking about some exogenous, endogenous ways to change our flow chart, and then potential effects of tumors, cancer. And we'll move on to insulin, talking about insulin and glucagon. So let's just draw out our flow chart. We got our hypothalamus. We got secretion of hormones from the hypothalamus. They travel a couple of centimeters down that portal system through that primary plexus. They make it to the secondary plexus that surrounds the anterior pituitary. And the anterior pituitary has receptors for that hormone. Therefore, it responds to that hormone by secreting more hormones. And those hormones get out into the system, go out to target cells, and those target cells will have a response. That response is typically compensatory, and if it's compensatory, that means whatever the response is, it's going to talk back to the original locations and say, we have too much or we have too little, because there's going to be receptors for that response in the hypothalamus and the anterior pituitary. If we really want to make this flow chart complete, which we typically do because we don't want to leave things out from one flow chart to the next, then we need to make sure we write stimulus on the top. So a great example, we'll just go ahead and use CORT. I mean, we could use thyroid hormone, CORT, it doesn't really matter which one we end up looking at, but we focused a little bit on thyroid hormone, so let's kind of move away and look at CORT again. I guess, yeah, sure, why not? What hormone will be secreted from the hypothalamus to start the chain reaction that will lead to the release of cortisol? Hormone is released from the hypothalamus. Help me help you. Yeah, we got TRH. We're going to just kind of leave the stimulus behind, but normally the stimulus will be stress in this particular case. What's the number one stressor in the human body? Just as a quick reminder, what's the number one stressor in the human body? Hypoglycemia. Great. So a lot of times on my test, I will make sure to just focus on that stress, hypoglycemia, and then you guys can think out in the real world about any other types of stressors and how it impacts your glucose levels and therefore how it might impact CORT release. But Stress in the sympathetic nervous system definitely act on cortisol, CRH. So now that's CRH transported to the anterior pituitary, and then what's going to be released down here from the anterior pituitary? ACTH. Good. ACTH acts on what gland is going to end up releasing cortisol? As a response, we're going to have CORT. So what gland secretes cortisol? Just the gland, the region of the gland, or just the gland in general is great, just a great start. Not the pancreas on this one, good try, but this is going to be a steroid. And the adrenal gland is the primary steroid gland in the body. The adrenal gland is. And what specific region, what specific and what specific zone? So it's going to be the adrenal cortex, not the adrenal medulla. Adrenal medulla is going to be norepinephrine and epinephrine. So it's the adrenal cortex. It's the outside portion, those 3 layers, GFR. And of that, it's the F portion. So it's the zona fasciculata. Redundancy, right? It'll come. It'll come. Some of you guys are throwing out answers, and I absolutely love it, right or wrong. Because getting things wrong in life is one of the best ways to learn. All right, so now we got our flow chart. This is nice. So it'll be very helpful in a lot of things you end up doing. Cortisol, of course, will end up having negative feedback pathways. You're saying glucocorticoid, right? Glutacoid. I'm guessing you're thinking glucocorticoid. So gluco tells us glucose. Corticoid tells us it's a cortisol. So cortisol is a glucocorticoid because what is the function of cortisol? It's to increase your blood glucose levels. That's why that implies both function and chemistry. Glucocorticoid. Corticoid. Now I can't say it. Did that make sense, Melissa, though? Cortisol is a glucocorticoid. Okay, cool. Whew. All right. So now what I'm going to bring to your attention is what if cortisol levels are, by disease standard, too high? This would be called hypercortisolism. And if they're too low, we call it hypocortisolism. You don't need to know those words for the exam or anything, but I'm just making sure that you guys hear those words to be able to think about those words because we're about ready to do that. Hypercortisolism and hypocortisolism. And then, of course, there's normal cortisolism, which would be healthy, go-lucky person. There are 2 diseases that are associated with these. I tend not to, I'm not going to test you on what is Addison's disease, for instance. I wouldn't do that. But Addison's disease is maybe a disease you've heard of before, but didn't know exactly what was going on. Or maybe this is your first time hearing about it. But this is one called, it's an adrenal insufficiency. So what do you think is going on with cortisol? Too high or too low in Addison's? Yeah, too little. And what do you think some of the symptoms might be for that now? What is the function of cortisol? What do we know about cortisol? Just trying to get you guys to think outside. Yeah, sure, it's an anti-inflammatory. That's going to be a side effect there, Becca. Just so you know, the primary function is to get the blood glucose up. Can you guys do that for me, pretty please? I know it's easier to remember as an anti-inflammatory and an immunosuppressant and stuff like that, but what I'm here to teach you guys is that most of the hormones in your body are all about energy, energy, energy. All right, cool. So when we start to think about maybe Addison's disease, right? And we start to think about some of the symptoms of Addison's disease, we might be able to see that there are specific things that are going to come about because, this is a nice one. This is a great one. Because you're not producing enough cortisol. So now we start getting certain specific side effects that might be related to that. For instance, weight loss. This is one of the first things that are going to come about, which seems strange at first. But how can you have weight gain if there's not enough blood glucose? Because glucose is essential for everything. We have to have an increase in blood glucose in order to store that stuff away as triglyceride or to make new proteins. Does that make sense? If you never increase your blood glucose levels, we can't gain weight. Does that make sense? So this is going to be one of the first signs of Addison's disease is just, weight loss no matter what the patient does. See that in some of these patient pictures. They're just, super skinny and they just have massive weight loss. Now, the opposite of this is called Cushing's disease or Cushing's syndrome. And Cushing's syndrome is excessive cortisol. There's tons of cort in the system. So what's going to be happening to your blood glucose levels all the time? Increase, decrease, no change. If cort's primary function is to increase blood glucose levels. So even though this person's going to feel stressed out, it's going to be a pretty miserable life. And at cort, increase gain weight, especially in areas where triglycerides build up. So definitely around the middle and around the buttocks and whatnot. And it definitely causes lots of different stretch marks. And it's something called a buffalo hump. Almost always results in a buffalo hump and what's called the moon face. So the moon face is weight gain in the face and the back of the neck. Again, none of this you will be tested on. I'm just teaching you guys this as a relevance. I'm not teaching you pathophysiology. I hope you guys see that. I'm just trying to teach you physiology to make the pathophysiology easier in your future. So then I throw the pathophysiology in there to make you understand the importance of the physiology. Does that make sense? This is just a real life example, so it sticks better in your brain. That's always worked for me. Now, the number one cause of Cushing's is actually Cushing's syndrome. And guess what Cushing's syndrome versus Cushing's disease means? Syndrome tells you that it's something that's reversible. The number one cause of Cushing's is cortisol injections. It's exogenous cortisol. It's a doctor throwing cortisol into a patient and causing hypercortisolism. That's the number one cause in the world of Cushing's. Crazy, huh? But let's go back to our flow chart and think about this. So exogenous cortisol would be an injection of cortisol. So literally, I am injecting exogenous, which means from outside of the body, cort. So what's happening to those cortisol levels? Increase, decrease, no change. Boom. And we do that over time too much, it's hypercortisolism, and that will cause Cushing's. By the way, if you were to look at this patient and you were to do a blood panel on this patient, what would you see with their CRH levels? If cort levels are high, what's going to happen to CRH? Increase, decrease, no change. And what's going to happen to ACTH? Increase, decrease, no change. Awesome. Awesome, awesome, awesome. The next major cause of hypercortisolism is a tumor. Okay, it's cancer. And I'm not going to go too much into what cancer is, but basically it's a cell that's learned to be immortal. Okay, they stop killing themselves. All cells go through a form of apoptosis where they go through in essence, self-suicide, self-assisted suicide, if you want to go that route. That helps you remember it. But if a cell bypasses the suicide, they can live forever. They're immortal. And then they replicate, and those cells replicate, and those cells replicate, and they carry that mutation through time. And there's two major types of tumors out there. One's called proliferative, and the other one's called destructive. A proliferative tumor is one where it goes in and it enhances those cells to secrete more hormone, and you can't stop it. It's proliferative. It's always going to be secreting a hormone over and over and over. You cannot stop it. It's broken. Destructive, you might be able to get it just from the term. If you have a destructive tumor of endocrine tissue, then it's going to destroy the ability of that tissue to produce that hormone. Does that make sense? Proliferative would increase hormone production. Destructive would decrease hormone production. Does that make sense to everybody? Awesome. So the next major type of hypercortisolism comes actually from a tumor of the anterior pituitary. And I'm going to draw in the tumor so you know it's a tumor. It's not a tumor. It is a tumor. I'm going to draw in that tumor with a gigantic arrow up. And as long as this arrow is up, I have a proliferative tumor of my anterior pituitary. What do you know is going to happen to cortisol? Because what triggers the release of cortisol? ACTH. So what's going to happen to cortisol? Increase, decrease, no change. So Veronica, when we're going down, and anybody else that might have had trouble with this, when we go downstream, this causes this. And there's nothing you can do about it. There's no negative feedback on cortisol because that's high. As long as this is high, this has to be high because ACTH is the trigger for cortisol release. Does that make sense to everybody? We're going down a waterfall. This leads to this. There's nothing you could do about that. So as long as ACTH is high, cortisol has to be high. Now let's look back on the feedback loop. If you were to do a panel on this patient, what would happen to their CRH? Increase, decrease, no change. Oh, okay. And what would continue to happen to ACTH? There's nothing we can do about it. You got it. It would be increased because it's proliferative. Does that make sense to everybody? What if there was a tumor in the adrenal cortex itself, in the zona fasciculata? Let's do that with a different arrow. We're going to do a gigantic blue arrow here. So what if I had a tumor here, a proliferative tumor here in the zona fasciculata? What would happen to cortisol release if I had a proliferative tumor in the zona fasciculata? Increase, decrease, no change. Got a massive arrow that goes up. This patient has hypercortisolism. This is another potential cause of Cushing's. A little bit more rare, but it does happen. Now let's do a blood panel. We know this patient has hypercortisolism because they come in, they have, the moon face and gaining weight in the belly and, red skin and a lot of the telltale signs. Patient's CRH levels, increase, decrease, no change. Due to negative feedback loops, as cortisol is too high, what's the body going to be doing to CRH? Increase, decrease, no change. Everybody on board with this? That this would be a decrease, just like if there was a tumor in the anterior pituitary. But now, it's going to be different than the anterior pituitary because there's no tumor here now. So it can react normally to negative feedback loops. So now when you look at ACTH levels in this patient, what do you know is going to happen here? Increase, decrease, no change. You got it. It's decreased. So do you see how even though both of those patients had hypercortisolism, they would have different blood panels and we would be able to distinguish where that tumor was found. And then, of course, we have to do further work, but at least it's non-invasive just by doing a relatively simple blood panel. Yes, no, maybe so? Now, very, very, very rare, but something we can think about. What if there was a proliferative tumor in the hypothalamus? If I had a proliferative tumor in the hypothalamus, how would this patient present? If we did a blood panel, what would happen to their ACTH? Increase, decrease, no change. And what would happen to cortisol? Increase, decrease, no change. So all three of these patients had hypercortisolism. All four, really, if you take into account the exogenous cohort too. But all of those different proliferative tumors would present with different blood panels, and we'd have a better idea of where the tumor might be and where we can start to localize it. Yes, no, maybe so? You could do the opposite for hypocortisolism. If there's destructive tumors, you can do the exact same kind of flow chart to be able to study that. Do you guys feel somewhat comfortable? This is by way, this is a case study. This is literally if you saw a patient that came in with hypercortisolism, how would you be able to determine where that tumor was at? Boom. Now you guys know. Real life. Simple arrows up and down. Anybody feel just a little bit smarter? Makes you think those endocrinologists, like, they're smart, very smart. They have to do a lot more work besides this, but there's definitely a way for them to get to the root of the cause a little bit quicker just by looking at physiology. Because physiology. All right, let's move on. So if you actually look at the lecture, some of the things that we haven't covered yet for thyroid hormone, I still want you guys to think about. Just because I haven't gone through them in detail doesn't mean they won't be on the exam, doesn't mean they won't be important. I have gone through them in roundabout ways. So for instance, thyroid hormone, primary thyroid hormone is increase energy or decrease availability. I guess I should say increase energy availability or decrease energy availability. Thyroid hormone. Good. I had a little lag there, so I wasn't getting your guys' responses. But yeah, it's all about increased energy availability, and it does that. Mitochondria. How do we know this? Genic amine or peptide. I'm getting some lag. Oh yeah, I see my side of the world is red bar. I'll do my best, hopefully. Yeah, I think a lot of people are doing this. Same, yeah. Yeah, I think it'll come back. So I'm back. I'm not red bar anymore. My sound. Alyssa, you're still red bar, but everybody else looks like you're back to being normal. Yeah, that was a weird. Yeah, Alyssa, you're super red bar on my screen, so I can see all of your guys' experiences. Your experience is poor. You're only getting 32 kbps. Your audio is at 18% and your video is at 27%. So yeah, Alyssa, you're having a hard time. Is everybody else back with me? Everybody else hear me okay? Yeah. Okay. Sorry about that. Alyssa, you'll hopefully you'll come around. Alyssa, if you can hear me, go ahead and reboot your Collaborate. Sometimes that helps. You tried turning it off and turning it back on again. Okay. Anyways, thyroid hormone's about ATP, But what I was asking you is what classification of hormone is thyroid hormone? Is it a steroid, biogenic amine, or a peptide protein? Good. Okay, quick and easy. It's biogenic amine. We've done this like 14,000 times. Not literally, of course. Now, is it nonpolar or polar? What makes this guy unique as a biogenic amine? Nonpolar or polar? It's nonpolar. And what do we know about nonpolar molecules? Where are their receptors? Are there receptors on the cell membrane, or are they cytosolic inside the cell? Good. Inside the cell. You guys remembering this about steroid hormones in general? Yes, no? And why was that important? Because if it has a receptor inside the cell, what is it always going to act on? The receptor inside the cell, what's it going to act on? The nucleus and DNA and protein synthesis. Does that make sense in terms of from last week? Cool. It can also affect other organelles that are inside the cell relatively easily. And one of the main ones that it acts on is mitochondria. Mitochondria is the powerhouse of the cell that makes most of its ATP. Cool? So we get new proteins. What are those new proteins? Sodium, potassium, ATP pumps. Why? Because those run your cells. Every single cell in the human body has sodium, potassium pumps, pumping sodium out of the cell, pumping potassium into the cell, constantly working on acting on the membrane potential, a lot of other functions you guys are going to learn about through the semester as well. Protein synthesis. It's making brand new pumps. Remember, all receptors, all transporters, active or passive, doesn't matter. Remember, those are proteins. Oh yeah, I am going in and out again. Let me try to reboot mine. Let me try to reboot my Collaborate. I don't know what's going on my side too. Let me try to reboot my Collaborate. See if that helps. I'll be back. All right, let's see here. Oh yeah, now I got full bars. Okay, I don't know. There was just a weird link going on there. All right, let me share my screen with you. Get rid of that. All right, don't forget that transporters, receptors, all of these functional units of your cell, those are proteins. So Heather was saying, wait a minute, it increases the number of sodium potassium pumps? Yeah, those proteins. So when I'm talking about protein synthesis, I'm talking about pumps and transporters, so forth, so on. Hormones, potentially. You guys on board with that idea? It's creating more pumps, brand new pumps, increases the actual number of pumps. Then they go to the cell membrane and then they move more sodium and potassium. They're also, as cells replicate, increasing the number of proliferation, for instance, those new cells need sodium potassium pumps too. All right, cellular respiration. Where did I write down that formula so I don't have to do it again for you guys? You guys kind of have an idea on cellular respiration at this point, I would imagine, where cellular respiration, take a breath in, oxygen in, eat some food, glucose in, phosphate stolen from your bone. All right, cellular respiration. Oxygen plus glucose plus ADP plus inorganic phosphate. Boom, we got some ATP, carbon dioxide, and and water is our metabolic waste. Yes, no, maybe so? Really important formula. You guys should know it. You must know it. You must know it. You must know it. You must know it. Now, ATP is the energy of the human body, and what do we know is produced as energy is burned? We make work, move skeletal muscles, move pumps, move whatever ATP is used for in the human body, lots of things. What's always a byproduct of work? What's always a byproduct? Heat, heat, heat. So the other thing is if I increase, we'll go ahead and do that, thyroid hormone increases ATP production and use. So if I have an increase in T3, T4, consumption, increase, decrease, no change. If I'm making more ATP, oh man, I'm red again. Man. Okay, I'm back. I was red. I'm having problems. I got problems. Can you guys hear me now? No, I think it's mine. It's probably because I got elephants on my roof. It's got to be the elephants. All right. While I'm good here, if T3, sorry, if ATP, if more ATP is being produced, what's happening to oxygen consumption? Increase, decrease, no change. Good. So oxygen consumption would increase. Call this increased oxygen consumption. We also call it an increase in oxygen demand because the more ATP you make, the more oxygen you need. So your body's going to demand it. So what's going to happen to your respiratory rate to get more oxygen into the system? What's going to happen to your patient's respiratory rate as they make more ATP? What about glucose demand? What's going to happen to glucose demand? Increase, decrease, no change. Increase. That's why T3, T4 is going to cause lipolysis. It's going to cause glycogenolysis. It's going to try to get more glucose in the system. Does that make sense? It's going to try to raise your blood glucose levels. See? Good. So this is really helpful because think about a patient that is hyperthyroid. How are they going to present? They're going to have some form of minor hyperglycemia. Their respiratory rate will be increased, and they're going to be hot all the damn time. They're super hot. Does that make sense? And if somebody is hypothyroid, what do you think is going to happen to their body temperature? What are they going to come into the doctor's office complaining about? They're cold all the time. Because their body's not producing enough ATP, they're cold all the time. Crazy, huh? T3, T4 does a lot more than the list that was on here, but we can kind of think about it in metabolism. We know we want to make more glucose. We want to get that Krebs cycle rolling. We want to make brand new glucose from amino acids, from glycerol. And then often we're going to want to use that to make more muscle. It's called a sympathomimetic. If something mimics something else, then it's going to copy it. Does that make sense in terms of the term? Is a drug or hormone that copies or tries to mimic the sympathetic nervous system. How does it do this? How I have to go talk to this herd of elephants. Make sure they're not messing with my internet. I'm back though. Everybody hear me okay? Everybody see the screen okay? Hi. Whew, what a pain in the patella. Okay. This is on the right side is a very important topic. You must know this, you must know this, you must know this. The fact that it's a sympathomimetic is really important because one of the primary things that it does is it's actually going to cause new protein synthesis and cause an upregulation, meaning an increase in the number of receptors for the sympathetic nervous system. Can you guys write that down somewhere special for me? Highlight it, underline it, asterisk it. Go get a tattoo of this. Don't really, please. Just tattoo your neighbor. No, don't do that either. A fake tattoo. But you got to know this. So if there's an increase in the amount of T3, T4 in the system, for instance, that is going to present with, you do have all of these lectures already, by the way. I'm gonna write this down though in terms of how it acts, if you don't mind. And then we're gonna be coming back and doing this more this semester. That's why it's so darn important. So just a second here. So if there's more T3, T4 in the system, if we have an increase in T3, T4, this causes an upregulation of primarily beta adrenergic receptors. But we're going to go with pretty much all adrenergic receptors for now. And if you guys will recall, adrenergic receptors are for the sympathetic nervous system. So if we have more adrenergic receptors, then it's going to increase the sympathetic nervous system activity. Does that make sense? And that's not a bad thing for short term, right? If we have T3, T4, you guys ever notice that, you know, anybody ever kind of have that idea of a kid that's bouncing off of the walls? Sense of your energy. I just need just a little bit, please. Well, what's going on with those kids is they're growing like crazy. And if you're growing like crazy, you need, oh man, I am glitchy. But what's going on with those kids? So sorry, so sorry. Tell me when you guys can hear me. Can you hear me now? Can you hear me now? Can you hear me now? Online format, most of the time it's good. I've never had this actually in the last 2 years where it's this bad. So it's got to be the roofing guys, right? We're just gonna blame it. We're gonna blame them no matter what. Let me finish that. We got, yeah, okay. Bro, you guys owe yourself the grade. That's the way we're gonna change that story around. You owe yourself studying hard, working hard, showing up for class, being present, and you will earn your grade. But kids that are growing fast, lots of T3, T4. That's what's going on. They have high energy because there's lots of ATP. They got this sympathetic activity going on. They're just wired, running around, going crazy. Boom. Now, let's think about that. If you're running away from Mr. Axeman, for instance, what's going to be going on with your heart? Increase heart activity, decrease heart activity. Oh, so what if somebody is hyperthyroid? What if they have a hyperthyroid issue? What are they going to be presenting with? Tachycardia. Yeah, fast heart rate's called tachycardia. So now we got tachycardia, we got an increase in body temperature. You're starting to see that there are telltale signs for somebody that is hyperthyroid. Yes, no, maybe so. Weight loss, because they're burning through their energy so damn fast. They're going through lipolysis and protein catabolism and stuff. So they got weight loss. What about somebody that's hypothyroid? They might present with bradycardia. They're cold all the time. They're gaining weight. Pretty cool, huh? Understand normal physiology and it makes the patho easier, not easy, because nothing in medicine is easy. Man, we have gone a lot longer than I wanted to go for thyroidism, but it is what it is. We got our flow charts. You guys now are better at understanding and reading these. True story. Stimuli, effects, and everything in between. Make sure you guys can draw these out. Try to avoid all the excess words, just nice, easy flow charts, and that will help you guys study them. Hypothyroidism, how it's caused, what sort of effects it might have. Hyperthyroidism. There's one more thing I want to talk about in terms of a cause for hyperthyroidism, which is called Graves' disease. This is actually not uncommon. And then I've already talked about goiters, so we'll come back to that. So let's talk just about these two things, Graves' disease, and then I'm going to just reiterate something with goiters because I often will test on it. So in order to understand, let's go back. Can you guys hear me? My status is bad, but okay. So we're going back to our flowchart we did yesterday. Nice simple idea. TRH is released from the hypothalamus, causes the secretion of TSH from the anterior pituitary, acts on follicular cells of the thyroid gland to produce T3, T4. Iodine is essential. Awesome. Now, what Graves' disease is, it's an autoimmune disorder. Autoimmune disorders are relatively poorly understood on why they exist and how they are triggered, and there's some crazy things going on out there. But autoimmune disorders are when your immune system starts to produce things that target your body. Your immune system shouldn't target your body. It should only target foreign things. But your immune system sometimes goes haywire and it starts to affect your body. So what ends up coming out of this immune disorder called Graves' disease is an immunoglobulin, which is basically a protein, right? It's a globulin. It's an immunoglobulin that mimics TSH. So this Graves' disease ends up producing something called TSI, which is a thyroid stimulating immunoglobulin. And this immunoglobulin bypasses TSH and constantly activates the follicular cells of the thyroid gland. So in this patient, what's going to be going on with T3, T4? Increase, decrease, no change, assuming they have enough iodine in their diet. Increase, decrease, no change. Increase. So they're going to act like a hyperthyroid. When we go back and do our blood panel, TRH will be low, TSH will be low, T3, T4 will be high, but it's because of an immunoglobulin. What else is going to happen leads into our other idea that I wanted to make sure that you guys just kind of what's the word I'm looking for? Re-examined. And that is a goiter. Remember what I taught you about a goiter is that as long as TSH is elevated, it will continue to stimulate the follicular cells, and the follicular cells will grow and grow and grow. True story? So as long as TSH is elevated, well, now we got TSI making TSH. We can't turn it off. Negative feedback doesn't act on TSI. It's your body going haywire. So this patient would also have a goiter. So the blood panel would show an increase in T3-4, decrease in TSH, but they would have a goiter, even with low TSH. And that's how you would know Graves' disease. That makes sense? Because TSH would normally have to be high. Or is that just because you can't hear me? I don't know what people's got to do with anything. With some. I can't hear. But pineapple. Gibber. Sorry, guys. We'll take a break here in a second. I'm going to try to. All right, I got full bars. Let's take advantage of it while we can. Pineapple. Felt it was like a safe word or something. Pineapple. All right. Let's see here. Sharing this. So what I was trying to say is that normally goiters would occur because TSH levels are high. But in this patient, their TSH levels are low, and yet they have a goiter. And that's a great way, a good indication that they probably have Graves' disease. Does that make sense? Even though you've done your blood panel, their TSH levels are low, but they have a goiter, you're going, what the hell's going on? Well, they got to have something else going on that's activating those follicular cells. Cool. Cool. We're done with all of those crazy hormones. Now we got one more crazy group of hormones that we must learn about. It's called insulin and glucagon. We got to know about these. We got to know about these. We got to know about these, especially insulin, because what disease is associated with alterations in insulin? Diabetes. So we got diabetes that's associated with changes in insulin. We're going to kind of try to fly through this, but I don't want to fly through it too much because this is such a critical part of your future. You got it, Tariq. You actually paid attention. We're going to go ahead and do a quick internet search because economic burden of diabetes. I looked it up recently, but I never remember the actual number. So as of 2017, the taxpayers are paying $327 billion to help treat diabetic patients. Number one health tax burden in the United States. If that doesn't blow your mind, I don't know what will. Diabetes is rampant. It is a disease that is affecting you and will affect you in the future, whether you have it or not. So just to raise a hands, who knows somebody with diabetes? Either type 1 or type 2, it doesn't matter. Who knows somebody? Yep, there we go. Look at this list. Da, 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 da. Everybody knows somebody with diabetes. And yet we don't think about it the same way as we think about cancer. You know, somebody gets diagnosed with diabetes, you're like, God, thank God it's not cancer. You know what I mean? It's just diabetes. We're good. Untreated diabetes is worse than most cancers, just so you know. Untreated diabetes is really, really bad for your body. And we're going to kind of think about some of the effects of diabetes, but not all of them. But not all of them. But we're going to see the effects of insulin through the entire semester, all semester long. We're going to see the effects of glucose all semester long. And I want you guys to be thinking about what would happen in patients whose insulin was broken. Again, if we go back to our list, because we did kind of a review of all the hormones, I think it was yesterday to start everything off, right? No, there's an elephant over our head, directly over my head. We did this list of hormones here, and we walked through it and we said increases energy availability, increases energy availability. Worse than cancer, because you got to remember most cancers are benign. And I got tumors on my leg. People hear the word cancer and they immediately go to the worst part of what cancer can be, which is these malignant metastatic cancers that will just rip your entire life apart. But most people have little tumors, and that's a cancer. So really, diabetes in and of itself, if it's left untreated, that person's going to die a really horrible, horrible death. And the reason why is because it's pretty much the only hormone in the human body that acts on storing energy away. And if we can't properly store energy away, we got issues, lots of them. It's almost always going to result in a ketoacidosis, and that's going to end up eating your organs away, and you're going to die of horrible neuropathies, and your respiratory system potentially can stop. And yeah, it's real bad. It's real bad. Yeah. Okay. So let's get back to this, and let's get back to this. You guys are a little bit more aware that diabetes will be a part of your future. Even if you're going dental hygiene, you got to worry about patients that have diabetes. They have gingivitis. They have worse teeth issues than anybody else. And you got to take care of that and be able to treat them differently than a normal patient. And you will see patients that are diabetic that are coming into your office. If you're going into nephrology, if you're going into cardiology, or if you're going into, childbirth and labor, right? You're going to have diabetic moms, and you better figure out that you got to treat them different than somebody else. Is this clear? Not different, you're treating them the same, but you know what I mean. I meant what you knew. Why is this? It has to do with exactly what I was talking about in terms of whether we store energy away or whether we're releasing energy. So glucagon versus insulin. There's something in physiology called the absorptive state. This is also known as the fed state. So absorptive versus fed. Right after you've eaten a meal, you're absorbing nutrients. Does that make sense? In your intestines? In your small intestines, you're going to be absorbing a boatload of nutrients. And therefore, what's going to start happening to the amount of amino acids, lipids, and glucose in your bloodstream? Increase, decrease, no change. And there's two things your body wants to do when you have excess nutrients. There are two things your body wants to do. Use it and store it away. Please write that down. If you have excess nutrients, there are two things your body wants to do. Use it right now or store it away. And what hormone is going to be released when blood glucose levels are high? Insulin or glucagon? Insulin, 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 insulin. So what did you just learn the function of insulin was? What are the two things your body wants to do when you have excess nutrients? Use those nutrients and store them away. So what is insulin's function? It helps us use excess it helps us use excess nutrients, and it helps us store those nutrients away. Does that make sense? Insulin is really important for using glucose right now, right after that meal. We got to use that glucose. We're going to make ATP. We're going to start making new proteins. We got energy right now. Let's not mess around. Let's use it while it's simple, while we don't have to try to steal it from a storage site somewhere. Now, glucagon is going to do the opposite. Glucagon is triggered with low blood glucose levels. And it's all about making sure there's enough glucose for the brain first and foremost. And that's why we can break everything else down. Make sure we have enough glucose in the system to run your brain during times of hypoglycemia. When we get too hypoglycemic is when we get hangry. You know, when you're so hungry, you're angry. And part of that process of hangriness is coming because glucagon is being secreted. And if you're not actually getting food into your body, then all you're doing is stealing from sources that your body has stored it away. Awesome. Now, insulin's the one we're going to focus on the most because insulin and diabetes go hand in hand. Now, the primary trigger for insulin release is an increase in blood glucose levels, and we've already covered that. But it's not the only trigger for insulin release. For instance, if you've eaten a meal of just meat, of just proteins, of just whatever, some protein source, a protein shake, you will get amino acids down in your small intestines, and the presence of those amino acids entering your bloodstream will also trigger insulin release from the pancreas. Last but not least, your gastrointestinal tract, your digestive system, is designed to monitor for glucose and amino acids. And literally just the presence of glucose and amino acids in the small intestines will trigger hormone release from the small intestines, and those hormones will act on the pancreas to cause the release of insulin. We've already covered this last tiny little portion here, the autonomic nervous system. But let me just reiterate this real quick. If you're running away from Mr. Axeman, do we want to store energy away? So what is the sympathetic nervous system going to do to insulin release? Activate or inhibit? A or I? Oh, hold on. You guys did this last time too, and I'm not sure what I'm doing with my terminology to make this wrong. You're running away from Mr. Axeman, so that's the sympathetic nervous system. True story? Do we want to store energy away? You guys just said no, right? We want to release energy, don't we? What's the function of insulin? To store energy away. So we don't want insulin to be active while we're running from Mr. Axeman. Helpful? The whole link, the flow chart of idea. Hopefully you guys will be able to pick that up. Insulin. We don't want that. It wants to use the energy. My bad. Sorry, maybe I did. I've known to miscommunicate in the past. So if so, I do apologize. I'll blame the Rubers for that too. Got to blame somebody else, right? Nobody ever takes credit in this life for their own mistakes. Pfft. I'm a true politician. All right. Insulin, we would want to inhibit that with the sympathetic nervous system, and the parasympathetic nervous system would activate insulin. Sweet. Okay, let's kind of skip this over here. Most target cells. We're going to be talking about what glucose uptake is and what GLUT4 is today as well. But if we're storing energy away, what do we want to do to the formation of glycogen? Increase, decrease, no change. The creation of glycogen. Good. What do we want to do to the breakdown of glycogen? Increase, decrease, no change. What do we want to do to making brand new glucose from something that wasn't glucose, like amino acids and glycerol? Increase, decrease, no change. What do we want to do to the formation of new triglycerides, new fats? If we want to store energy away, what are we going to try to do to those triglycerides? And triglycerides need fatty acids for their function. So in order to make new lipids, we need to get those fatty acids into the cell. That's called uptake. So if we're moving something from the blood, this is an important word students will often mess up. So you might as well write down the definition of uptake in physiology. Uptake means we take a nutrient from the blood and we put it into the cell. We're moving it from the blood into the cell. What does uptake mean? Moving a nutrient from the blood into the cell. So in that same regard, if I have an increase in blood glucose levels, and the function of insulin is to decrease those blood glucose levels, the reason why it can decrease those blood glucose levels is because it takes the glucose from the blood and it shoves it into the cells of the body, including adipocytes. This is called glucose uptake. So as we increase glucose uptake into cells, that means there's less glucose in the blood and blood glucose levels start to drop. Does that make sense? Is anybody confused by that? We will draw a flow chart out. Sure thing, you got it. As blood glucose levels increase, I think we have something written down somewhere about this. Yeah, I want to say pretty good at this through the semester, but we do. As blood glucose levels increase, it causes insulin to be released. As insulin is released, its effect on the blood glucose is to bring it back down again. But how can it bring blood glucose level back down? It's going to take the glucose that's in the blood and it's going to shove it into the cells of the body. That's called glucose uptake. So as glucose uptake increases, we're moving glucose from the blood into the cells, and that's why blood glucose levels drop. Does that make sense? Awesome. And we're going to draw it out again. No worries, no worries. We will draw that out again. We're going to do it today. We have to finish the endocrine system today because I need to be able to start blood today in lab and then finish blood and blood clotting tomorrow in lecture. So got to get done with this. So cool. Now you kind of have these impacts on the liver and adipocytes. There are what am I saying? Let's not forget what makes a target cell a target cell. Oh, receptors. So there's something called an insulin receptor. Where are we going to find insulin receptors? Liver, adipocytes. Does that make sense? And then we're going to have some other target cells as well you guys are going to learn about. You guys good with this idea? Never forget that little blurb, what makes a target cell a target cell. If an organ is going to respond to a hormone, it has to have a receptor for that hormone. Okay? I'm going to come back to this. But in almost all the target cells for insulin, it's going to drive glucose into those cells. Awesome. We need that. We need to take all of the glucose from your meal and just start to push it into the cells of our body. And the reason it's going to be able to do that is due to a specific transporter. We're going to come back and talk about in detail. You must know this. You must know this. You must know this transporter. In addition to glucose uptake into your cells, we also need acid uptake because we need to make new proteins. If we make new proteins, then we're using energy because we're making ATP with the glucose that's going into those cells, and that ATP can help drive chemical reactions to make new proteins. So we want to do as much protein making as possible after a meal. One of the important things about not skipping meals. Your body needs protein, it needs receptors, it needs transporters, it needs other hormones. And I dropped again. Where did I stop? I'm not looking at the screen. We're gonna take a break because I'm starting to get into the hard stuff. Oh, you didn't even notice a glitch? Oh, nice, cool. Did anybody notice a glitch? Because I glitch. Okay, cool. Sometimes that happens where you can hear me the whole time. Okay. So good. Yeah, I haven't changed the slide at all. So I'm going to change the slide now. Just a nice flow chart. I love my flow charts. I love them. So I found this great one right here that goes and literally says exactly the same thing as this slide of a ton of words says. Trigger for release, blah, blah, blah. Well, let's look here. What is the trigger for release of insulin from the beta cells of the islets of Langerhans? Well, primary release is increase in BGL. What else can trigger insulin secretion? Amino acids. So if you get amino acids in your bloodstream, it will tell those beta cells to secrete some insulin. What else? Well, the GI system. Just eating some food will trigger the parasympathetic nervous system, or just having a little bit of glucose or amino acid in your digestive system will cause hormones that you don't need to know yet to be released to trigger the release of insulin. So it's summarized in this flow chart as well as this list. Last but not least, running away from Mr. Axeman, what's that going to be doing to insulin secretion? Well, we don't want to store glucose away, so we want to inhibit insulin secretion when you're running from Mr. Axeman. Cool? You guys starting to appreciate flowcharts maybe a little bit more? And if not, I'm sorry. That's why I give you guys all these other things if you're not flowchart people. I love flowcharts. Last but not least would be a combination of flowcharts and diagrammatic forms. So the primary stimulus for insulin secretion is increase in BGL. What does it do? Blah, 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 blah. What are the target cells? Liver, adipose, skeletal muscle is going to be a big one. Most cells of the body do have insulin receptors. And in any cells that do, it's going to increase glucose uptake. Yeah, it just makes things so much easier to memorize. I'm not the smartest person in the world. The way that I retain all my information is by abbreviating the hell out of it, learning the key words, and then being able to be kind of a storyteller. So that helps. So I can kind of elaborate on keywords. All right. So how does glucose uptake happen? And that's what we're going to do next. We got a couple things, relatively difficult ideas to talk about, but guess what? If we break them down by starting with scratch, we can do this, I promise. So what we're trying to do is we're trying to learn how things happen. That's what physiology is all about. We're not just saying A happens, therefore B happens. We want to say, how does A cause B to happen? What do I mean by that? If there's an increase in blood glucose levels, what hormone released via this increase in blood glucose level? What hormone is going to be released, y'all? Insulin. So when there's an increase in BGL, there's an increase in insulin getting into the blood. We got a problem, though. We don't know how. How? How does an increase in blood glucose levels cause an increase in insulin? How? You need to know this, because if the how breaks, what's going to happen to insulin secretion? Increase, decrease, no change. And now we got diabetes. Next. What do we know the function of insulin is? What's it going to do to blood glucose levels? Increase, decrease, no change. How? 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 We got to know how, because what if the how breaks here? We can have as much insulin in the world as we want, but what's going to happen to your blood glucose levels? They're going to stay elevated if we can't bring them down. Does that make sense? So we need to answer these two questions. How does an increase in BGL increase in insulin, and how does that increase in insulin cause a decrease in blood glucose level? We're going to do that via just small diagrams. So in order to understand this better, we're going to draw a diagram. I'm going to draw a blood vessel. Sweet. I got plasma. And what's going to be happening in my plasma? Exactly what we wrote here already. We eat a meal or whatever, right? Primarily eating a meal. Eat. And when we eat, our blood glucose level is going to increase. We're going to learn more about how that happens in the digestive system, but blood glucose levels just went up. These blood glucose levels are going to have to get read somewhere. What organ secretes in? Oh no, I'm red again. I'm going to cry. I'm going to cry. Okay, I'm kind of back. I know, I froze. I'm so sorry. What organ secretes insulin? I'm just going to cry. My poor. I love pancreas. Pancreas is my favorite. The beta cells, the islets of Langerhans. Great job in the pancreas. You guys got it. So what we're going to do right now is we're going to kind of bypass this how, and we're going to move over to this how. It's a little bit easier to understand. So this BGL is going to be read by the pancreas, and we're going to learn the how of this. And in response, the pancreas will secrete insulin. So now we have insulin in our bloodstream, and we're going to go ahead and just put insulin, I don't know, a green star. So now we got insulin in our bloodstream, and it's being transported because it's a protein, so it just dissolves in the plasma, and it's going to move through the body. Target cells can be anywhere the blood. Awesome. When it gets to its target cell, it's going to move out of the bloodstream. You'll learn how things move out of the bloodstream in the next unit. So it's going to move out of the bloodstream, and now we have insulin in the interstitial fluid. I'm red on my side, so I'm worried that you guys can't hear me again. Can you hear me now? You're back. Man, this session, rawr. I'm going to put a sad face on my, I'm sad. If you look at my status, it should show like a little sad face. I'm super sad. Insulin's getting into the IF. Now, the IF is just that communication zone between the cell and the plasma. So here on the cell, again, what makes a target cell a target cell? A receptor. So we're going to have a receptor for insulin. This is called the insulin receptor. It's called IR. So now IR, the insulin receptor, you guys don't know too much about it. That'll be for more like a cellular physiology class. But so on the inside of the insulin receptor, there's an enzyme, and that enzyme will be activated in the presence of insulin. And then that enzyme is going to have cascade, going to go down and impact the inside of the cell. Without going into too much detail about what it does, I'm going to go ahead and say it helps drive exocytosis. So it's going to cause exocytosis of something. Okay, so this insulin receptor, when it's activated, it's going to help with exocytosis. Exocytosis of what? So that takes a little bit of review to be able to better understand. I'm going to just use the blank space that I have on here. So back in A&P1, you guys were taught about different types of transporters. Doesn't mean you remember them all, so that's why I'm reviewing it. But there are two major types of transporters, passive and active. You guys with me so far? There's a primary active. The primary active transporter always directly uses ATP. There were secondary active transporters. I'll end up having to describe these in a little bit more detail here soon. Secondary active transporters use the by the primary active transporter, but I'll draw that out. You guys will understand it. You'll have to for this semester. It's an important one. There are actually tertiary and quaternary active transporters. It gets really complex. But the secondary active transporter uses the kinetic energy. Remember, kinetic just means passive. Everything in the universe is trying to go from an area of high to low. And that's what kinetic energy is. It's the energy of motion, kinetic energy created by primary. Sweet. So the primary is going to be moving things up its concentration gradient, creating kinetic energy, and then the secondary active transporter gets to use that. Now, passive, on the other hand, we can have just simple diffusion. Well, we're not dealing with that here, but we want to make sure that we have it on our list. Simple diffusion, like a lipid, right? That can just go right through the cell membrane. It's simple. Oxygen, an example of simple diffusion. It just moves wherever the hell it needs to go because it's so small and it's nonpolar. But the other major type of passive transporter was called facilitated diffusion. Do you guys kind of remember somewhere in your memory chambers this word, facilitated diffusion? Maybe, maybe not. If not, no worries. Again, that's why we're here. That's why I try to get you guys on the same page. But the similarity that you see in these words is diffusion, right? Diffusion tells us high to low. Active tells us low to high. Kinetic tells us high to low. But we're always going to be able to go with active. There's always something moving from low to high, no matter what it is. It's always low to high, and passive will always be high to low. Cool? Everybody cool so far? I got more to do. I'd love to give you guys some good breaks and then still get into some blood today. All right, so diffusion here, low. There are a number of different facilitated diffusion transporters out there you'll need to learn, but the most important one that you guys are going to have to learn about has to do with the transport of glucose. Okay, so as an example, as an IE, you guys must know this transfer. It's called capital G, capital L, capital U, capital T. It's called GLUT. Glucose, GLU, glucose transporter. Capital G, not lowercase, capital, 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 capital GLUT, GLUT. So if I were to draw this in a cell membrane, okay, it's going to be one of these C-shaped facilitated diffusion type transporters. If glucose is high out here, and I have a GLUT transporter here, is going to go into the cell, or is it going to leave the cell? Remember, it's always going from high to low. Exactly. Good. So in this case, glucose would be transported. It's facilitated. It's helped by this transporter. It's going to be able to move down its gradient into the cell. But what if the amount of glucose out here decreases and the amount of glucose inside of the cell is relatively high relative to the blood out here? What direction would glucose go in this example? Into the cell or out of the cell? Ugh. Do we ever want glucose leaving our cells? Not really. In the liver, that's fine because liver is constantly bringing glucose in and throwing glucose out. You guys are going to learn some tricks for osmosis. So this isn't exactly like osmosis, but basically it's using a transporter to move things around though. So always high to low. Your skeletal muscle and your adipose tissue, that sort of stuff, we don't want to be losing glucose because glucose is essential for making ATP. So do you want this GLUT in your cell membrane all the time? Only in certain organs of the body, not on all of the organs of the body. It gets complex. It gets pretty cool though. So how does the body go about trying to work with this crazy transporter that's helping to mobilize and move glucose to where it needs to go? Well, we have these things called isoforms. So GLUT, there are numbers of different types of GLUTs. There's GLUT1, there's GLUT2, there's GLUT3, there's GLUT4, and there's GLUT5. There's more transport than this, but these are the 5 you guys need to know. So let's go ahead and write these on another page. Pineapple right now for I show good signal on my side for the first time today. GLUT1, GLUT2, 3, biscuit eater, GLUT4, GLUT5. Let's take a break then. Well, you guys probably can't hear me. All right, I've been watching my stuff, and everybody's got red bars. Like literally, you look at, yeah, Blackboard's just having issues today. Can anybody hear me? Probably not. Yeah, I mean, I'm looking at everybody's bars, and it's like poor experience down the board. Glitchy. Blackboard's super glitchy. We'll try to get everybody back up and running. I'm still audio loss is at 42%. So you guys should be able to see my screen just fine. You just keep losing my audio. Is there another way to do this? No, not that I have handy. No, I do things different every time. So just bear with me. I'm so sorry. I wish there was I could do about it. I'll be right back. So let's go ahead and get going here. I know how Blackboard works with me is that just, when I reboot, it seems to always work, at least for a short period of time. Try connecting to your cell phone hotspot. I don't have I don't know. Now that I am Jerry and I don't exactly, I've never really used hotspots too much. So maybe outside of class Tariq, you can teach me how to do that. But for this go around, it would be too big of a pain of a pain of the patella. So let's just get rolling here. We'll be good. We'll be good. I know it's not the best, and I apologize. But what I want to remind you guys of is that we have a facilitated diffusion transporter called GLUT. And what I was saying when everything was going awry is that there are multiple types of GLUTs in the body, and this is how the body can control how glucose is transported in and out of cells, because we don't want this GLUT to be in the cell membrane of every cell of the body all the time, because glucose would just go whatever the hell direction it wanted to go based on high to low. So we need to regulate it by having specific GLUT transporters in locations. So for instance, GLUT1 is only really found on the blood-brain barrier, the BBB. So that way, it's always present. This guy here, always present in the membrane. Why is that important? Because we are constantly trying to increase our blood glucose levels enough so that glucose is higher in the blood than it is in the brain, and we're trying to drive glucose into our brain all the time. So GLUT1 always needs to be present in the blood-brain barrier so that glucose can move from the blood to the brain. GLUT2 is one we're going to talk about very often this semester. Okay, GLUT2 is found in places like the liver. GLUT2 will be found in places like your kidneys and your small intestine. So GLUT2's some pretty darn important locations, and it is always present. Okay, this one is also always present. I'm just going to go ahead and put an asterisk here with the always present. So now we got a key. If things are always present, I'm going to do this pink star. GLUT3 is found in a number of locations, but the primary one you guys should know about is it's found on neurons. Neurons always need glucose, and they're always going to be going from high to low because they're going to be burning through glucose, and therefore the glucose inside those cells will always be low. GLUT4, this one's cool. It's very unique. GLUT4 is found primarily on adipose, so that's fat cells, and skeletal muscles. It's not only found here, but these are the primary locations: adipose and skeletal muscle cells. These ones are tricky. These ones are tricky. Why are they so tricky? Because think about what we talked about, the fed state and the fasted state. If you've just eaten a meal, where do we want to drive all that glucose? BBB's blood-brain barrier. Yep. Pink asterisk means that it's always present in the membrane. Means that it's always there. This will make more sense in just a second. No problem. What were we saying about the fed state? Is that in the fed state, our blood nutrient levels are high. There's a lot of glucose in our blood. There's a lot of amino acid. There's fats in our blood. And what do we want to do with all that excess glucose and with those excess amino acids? We want to move them into the cells. We want to store it away and use it. And we call this uptake. Does that make sense? So when glucose goes from the blood into neurons, we call it uptake, so forth, so on. Now, in adipose and skeletal muscles, what about when blood glucose levels are low? When you have hypoglycemia, then we need to steal the glucose away from these cells, but not from these cells per se. We're going to be breaking fatty acids down. We're going to be breaking skeletal muscles down, but we're going to be releasing amino acids and fats, not glucose. These cells hold on to their glucose. They're kind of glucose gluttons. And as such, we don't want this GLUT transporter to be in the cell membrane here all the time. During periods of hypoglycemia, the cell wants to clean the glucose. It doesn't want to give it up. And we said over here, if blood glucose levels are relatively low relative to the cell, glucose would leave as long as a GLUT is present in the cell membrane. So what we do here instead for GLUT4 is these ones here. All GLUT4 transporters are known as insulin dependent. These are insulin dependent transporters. Kind of semi-inaccurate. We're going to learn another way that GLUT4 can be upregulated, but insulin is required for most GLUT4 activity. These are insulin dependent. Don't worry, we're going to come back and kind of finish this thought process off with our flowcharts. This is just a piece of the puzzle. So in order for GLUT4 to be in the cell membrane, insulin also needs to be present. Again, in order for GLUT4 to go to the cell membrane, what hormone is going to help the upregulation of GLUT4 to the cell membrane? What hormone does that job, y'all? So as long as insulin is present, it's going to cause GLUT4 to upregulate, which means there are more GLUT4 transporters in the cell membrane. So that was that word upregulation we learned the very first week of class. GLUT5 is an interesting one because GLUT5, even though it says it's a glucose transporter, remember there are a lot of different types of monosaccharides. There's glucose, galactose, which is found in milk, and then there's fructose. And GLUT5 actually doesn't transport glucose. It only transports fructose around. And we're going to learn more about this fructose in the digestive system. Fructose acts similar to glucose. But you may or may not have heard of this whole, high fructose corn syrup ordeal that's going on in the world around you. Don't eat foods with high fructose corn syrup. You might, you read that on the labels. No high fructose corn syrup. You guys know what I'm talking about? Big fight out there in the world about fructose. And those high fructose corn syrup companies are saying a sugar is a sugar is a sugar, which is true. Your body uses all sugars the same: fructose, glucose, galactose. They all get used for the same thing, making ATP. But we have different transporters to move them around. That's something that those big money businesses will never tell you. And that will impact diabetes and weight gain in the long run. We'll learn more about that in the digestive system. But for right now, and for this unit, there are two of these transporters you need to focus on. You need to study GLUT2. We'll be talking more about that. And you'll be studying GLUT4. And this is going to be most of your semester. You'll be dealing with these two. Okay. GLUT2 is always present. GLUT4 is insulin dependent. As long as insulin is in the system, GLUT4 will be upregulated. If there is no insulin, GLUT4 will be downregulated. Does that make sense? Just the terminology, just the puzzle pieces. Okay, cool. So the way this works then is that a cell actually already has GLUT4 made. It's insulin dependent. Well, it's a receptor. Insulin receptors are proteins. So if I have a protein, what does the cell store proteins in and on? It's a protein. It can't just go through the cell membrane, and it can't just get moved to the cell membrane on its own accord. So what do we know about proteins, whether it's a hormone, whatever? Exactly. The Golgi apparatus is going to make GLUT4. GLUT4 is made here, and then that GLUT4 is stored on a vesicle. And if I have exocytosis of a vesicle with GLUT4 on it, then that vesicle fuses with the cell membrane, and all of those transporters insert themselves into that cell membrane wall. This is called GLUT4 upregulation. And boom, once we have GLUT4 in the cell membrane, what can be transported through GLUT4? What nutrient is transported through GLUT? Anybody? Everybody? Glucose. You got it, glucose. So now we had this increase in blood glucose over here, but this GLUT4 is going to allow glucose that was in that bloodstream, it's going to go into the cells at this point. And this is called glucose uptake. Glucose uptake. Yes, GL stands for glucose, and T stands for transporter, Heather. So GLU, glucose, T, transporter, glucose transporter. Did you say the Golgi makes or carries it? The Golgi packages it, Alyssa. The Golgi apparatus packages all proteins, peptides, into vesicles. Yep, it's the post office. It puts a stamp on it and tells it where it needs to go, but then it's going to need a signal. It's going to need that UPS carrier to move it to where it needs to go, and that's what this insulin receptor enzyme is going to help do. Perfect. And that's going to drive exocytosis of GLUT4. GLUT4 upregulates in that cell membrane, and once it does, glucose can now enter the cell, and we call this glucose uptake. So what's going to start happening to the blood glucose levels is glucose is moved from the blood into the cells. What's going to happen to blood glucose levels? Increase, decrease, no change. Decrease. Good. Isn't that what we asked for in the beginning, right? If there's an increase in blood glucose levels, there's more insulin. As insulin is present, it drops those blood glucose levels. How? Well, the how of this is insulin acts on an insulin receptor, which now activates an intracellular enzyme that drives exocytosis of GLUT4, causing the upregulation of GLUT4, therefore allowing for glucose to enter that cell, called glucose uptake, which drives the blood glucose levels down. Do you guys see how that would work? Exactly, Heather. Technically inactive because it's not in the cell membrane. And that GLUT4 will be stored on a vesicle until it's told that the cell needs more GLUT4. And what hormone is going to tell GLUT4, go to the cell membrane? What hormone, everybody, is going to cause GLUT4 upregulation? Insulin. 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 So let me ask you guys, what would happen in a patient where the insulin receptor, no, not only adipose and muscle cells, Heather, sorry I didn't emphasize this strongly enough. I said primarily. There are definitely other cells in the body that have GLUT4, but we're going to focus on adipose and skeletal muscle tissue for the exam because there's already enough for y'all to learn. Let's go in here with actually a different color than this. I don't know, this cool orange color. What would happen in a patient that the insulin receptor broke? What's going to happen to the upregulation of GLUT4? Increase, decrease, no change. Therefore, what happens to glucose uptake? Increase, decrease, no change. Therefore, what happens to patient's blood glucose levels? Increase, decrease, no change. Okay, when we break insulin receptor, okay, decrease in insulin receptor activity caused by a disease, this is called diabetes type 2. Okay, type 2 diabetes is when the insulin receptor no longer functions properly. What causes type 2 diabetes, everybody? Breaking what? The insulin receptor. And there's all sorts of reasons, whether it's a genetic disorder that decreases the number of insulin receptors that are available. But the primary reason why the insulin receptor decreases in its activity is through a process called desensitization. Okay, primary cause of type 2 diabetes is desensitization. Desensitization. And what that means, yeah, we'll get there right now. We're on our way. Is what do we know is activating the insulin receptor? Let's work our way backwards so you guys can use logic and common sense. What is activating the insulin receptor? Go ahead and write out the full word for me. Just redundancy thing. Insulin. And what's the trigger for insulin? What causes? What's the stimulus? An increase in blood glucose level, mostly food. So if I'm eating often, and if I'm eating a high carb diet, what's going to be happening to my blood insulin levels? Increase, decrease, no change. And doing this every hour or every 30 minutes, if I'm eating lots of high carb snacks, my insulin levels never get a chance to come back down again. Does that make sense? Insulin remains high in my body throughout the entire day because I'm snacking and eating all the dang time. I'm eating McDonald's, high carb meals kind of thing. Is everybody on board with this? And this insulin receptor is going to be active. As long as insulin is in the system, the insulin receptor is active. And over time, this insulin receptor is like, F this noise, man, I'm going on vacation. Permanent vacation. And it starts to downregulate and it starts to desensitize. It's like, dude, I'm done. What are you doing? I'm done. And this is type 2 diabetes. And depending on how much that insulin receptor has gone on vacation, that's going to lead to the different progressions of type 2. You guys don't need to know all the progressions of type 2. That's not the purpose of this class, but pretty cool to think about, right? I think it's pretty cool. I think it's pretty cool. So you guys have answered that how one more how to go through. Here's the the slides that I actually have, right? As long as insulin is not present, GLUT4 will be on the vesicle inside the cell. But as long as insulin is present, it will bind to this tyrosine receptor kinase. This is an enzyme, a receptor enzyme here, and that's going to create a signal cascade that drives exocytosis of GLUT4. Now, as long as GLUT4 is present in the cell membrane, glucose can enter that cell. Boom, we're dropping that blood glucose level down. By the way, one more thing actually that's really cool. There is something else that can cause GLUT4 upregulation. There is one other thing on the face of the planet that I know of besides pharmaceuticals, we're not going there, one natural thing that will cause GLUT4 upregulation. Let me ask you guys it this way. What ion do we know is essential for exocytosis? What ion will be increasing inside of this cell? So after all this cascade, the signal cascade stuff, we know that calcium is going to increase inside of this cell. So what is muscle? Is there another way to get calcium to increase inside of your cell other than a signal cascade driven by insulin? And I hope you guys remember from AMP1 that at the neuromuscular junction, when we have exactly at the neuromuscular junction, once we activate those ryanodine receptors on the sarcoplasmic reticulum, then that sarcoplasmic reticulum dumps calcium out everywhere, doesn't it? Yes, no? Yeah. And calcium levels inside that cell have to increase to allow for muscle contraction to even occur. And now we have calcium in that cell, and we can start to drive other exocytotic functions like the 4. And Heather, you got it. Head on the nail right there. Nail on the head? Yeah, that's a better way of saying the phrase. The answer. Nope. It'll come back. This one will come back. This is not the red signal. This is just a glitch that happens. From my experience, I don't normally get the red signal. This normally happens at least once per letter. You guys got me? You got the video back now? Audio feed, video feed, all back? Yeah, so Heather, you got it, right? You got that the what is it when you hit the head? That's what they say. Is that what you can tell a type 2 diabetic? If they are hyperglycemic, well, man, you can try to give them excess insulin. That's one way to do it. You give them more exogenous insulin. So few receptors that are there are more likely to get activated. Or you tell them to exercise. Go move. Get your butt up. Go walk. It doesn't need to be anything crazy. Just exercise. And as you exercise, the glucose will go from your blood into your cells because exercise causes GLUT4 upregulation. Pretty cool, huh? I love that part of the story. There are things you could do for people. So if you have a diabetic family member and they are chronically hyperglycemic, help them. Help them get off the couch. Help them go for short walks. It doesn't take much. Just a little bit of motivation. Cool pictures of upregulation and stimulation, but don't worry about this. You guys can look at this outside of class. Now, let's be done with this with one more slide. Then we'll take another short break, and we're going to talk about blood. You guys deserve it. The other break, especially with all of this problems with the internet. Problems? Do you remember how we started? How is that when there's an increase in blood glucose levels, it causes a release of insulin from the beta cells of the islets of Langerhans? Yes, no, maybe so. And then I said, but how? We haven't answered that problem yet. So what we need to do is we need to answer that. We need to answer what's happening in the pancreas in the presence of glucose. You guys ready? I'm going to do this in a way that I know works. Students can follow this. I promise you'll be okay, because you've had actually a lot of information to understand this system. We just need to tie all those puzzle pieces together. So first and foremost, stop reading all of this. Stop. Stop. Right now, stop. What do we know the beginning of the story is for this? What's going to end up causing the release of insulin? What did we say the beginning of our flow chart is? An increase in blood glucose levels. Lovely. So you already know the beginning. What's the end going to be? What's the end of the story going to be? I love doing this, by the way. It's a really helpful way to understand. No, that's the far end. I'm so sorry, I did not specify. The end of this flow chart is going to be the release of what hormone? Not exocytosis yet. We'll get there. But look again here, right? The beginning of the story is an increase in blood glucose, and what is going to be the end of the story we are going to describe is an increase in not GLUT4 yet. We're not there. Just work with me. We're trying to answer this how, right here, this how. So when there's an increase in blood glucose level, this is going to cause an increase in insulin in the blood. We're asking, how does that happen? So the beginning of the story is an increase in blood glucose level, and the end of this story will be insulin secretion. Does that make sense? Sorry for the miscommunication, but we're there. We're there. Okay. Okay. Beginning of the story is glucose. The end of the story will be insulin secretion. Yep, the macro story we'll get to. We're going to tie it all together. Not a problem. I completely understand where you guys were at. But I want you guys to be thinking both forwards and backwards, because once you can do that, once you can use what you know, man, this stuff becomes much easier. So what ion do we know is essential for exocytosis? What ion? What ion? We just went through this. What ion is essential for exocytosis? It's calcium. Okay, that's literally what we just went through. All exocytosis requires calcium as a secondary messenger for its function. All exocytosis in the human body kind of tells you the importance of calcium. Your brain, neurotransmitter release, hormone release, man, all sorts of things require exocytosis, therefore calcium. Wow. So if we know that there's going to be insulin in our blood, and that insulin is a protein hormone, then it had to have been stored on a vesicle. And in order for that vesicle to go through exocytosis, what ion is required for that function? Calcium. You guys with me so far, going backwards in this story? And where is calcium normally higher? Outside the cell or inside the cell? Based on AMP1, or if you don't know this, follow along as best as you can. Where is calcium normally higher? Outside the cell or inside the cell? A lot fewer people are answering this, so you just don't know, apparently, which is fine. Y'all, calcium is higher outside of the cell. Yeah, I don't know. Perfect, Becca. Let me know that. Calcium is always higher outside the cell. Again, remember the neuromuscular junction. There's more calcium outside of the cell because the SR doesn't count as inside the cell. It's not part of the ICF. Sodium's high outside. So sodium's high outside, calcium's high outside, chloride's high outside. The only thing that's high inside is potassium and proteins. Ooh, you guys need I don't want to spend too much time reviewing this right now, but well, yeah, we'll deal with that later. So right now, just learn calcium is higher outside of the cell, and then when we get to cardiac system function, I'll teach you why. Around. So where is calcium higher, everybody? Outside or inside? O or I? Awesome. Therefore, if we want to move calcium around, it's going to go from an area of high to low. What we need is a channel for that function. What we need is a channel for that function. Just let me do one more quick refresher because students tend to need this. Hey, man, so many. It's the beginning of all A&P2. Every semester, there's always going to be some review stuff, and that's fine. So who remembers this picture as I'm drawing it here? Yeah, we got our terminal Bouton or synaptic terminal or whatever the heck you guys learn it at. We got our motor end plate and our T-tubule. So this is something that hopefully you drew out a number of times in A&P1, so it should be a little bit stronger of a memory. And what you guys learned is you have an axon in this terminal Bouton right here, and then you had an action potential that came down that axon, and it activated a voltage-gated calcium channel. Is this kind of ringing a bell? I hope your professors taught this. If not, give me their names. No, don't really. And when we activate, A with an arrow up means activation. When we activate the voltage-gated calcium channel, this is an action potential, now calcium moves into that terminal Bouton and allows for exocytosis of that neurotransmitter. Yes, no, maybe so, based off something you guys might have tickle in the back of your memory. So calcium is always required for exocytosis. Where is calcium higher? Outside the cell. And if we open up a channel to allow calcium to enter, one of the best ways to do that is with electricity, just like at your neuromuscular junction. Okay, so if we go back here to our picture, what you'll notice is this is exactly like the terminal Bouton. There is a voltage-gated calcium channel. If we activate the voltage-gated calcium channel, then calcium enters the cell. Calcium drives exocytosis and release of insulin into the blood. Does everything here make sense so far? Don't worry about everything backstream. We'll come back there. We're going to go to the end. We're going to go to the beginning. Then we'll fill in the middle because the middle's the hard part. Cool. Next, glucose, pancreas. These are the beta cells of the islets of Langerhans in the pancreas. So as blood glucose level increases, glucose is going to go from an area of high to low as long as we have a transporter in place that allows glucose to move from high to low. And what transporter did we just review? Not the insulin receptor, that's for insulin. We need to move glucose. And this is not a glucose-dependent cell, because, sorry, this is not an insulin-dependent cell because it releases insulin. We can't have it be dependent on insulin. Okay, you guys are jumping guns here. Let's go back to our list. We'll add the term to it here. There are GLUT, G-L-U-T. GLUT allows glucose to go from high to low. Yes, no, maybe so? Let's go ahead and add pancreas to our list here for GLUT2. But GLUT1, GLUT2, GLUT3, GLUT5, these guys here are always present. They are not up or down regulated. They are not dependent on insulin. We don't want all of our GLUT transporters to be dependent on insulin, especially not ones on the pancreas, because the pancreas releases insulin. So you can't make the pancreas dependent on insulin if it secretes insulin. Does that make sense? That's just counterintuitive. So we can't have GLUT4. This is insulin dependent. It requires insulin for its up and down regulation. So instead, the other one I told you guys to focus on exists. This one's GLUT2. GLUT2 is always present. GLUT2 is always present. And as long as it's there, glucose can go from an area of high to low. So while we have high glucose that glucose starts entering the cell. And what's going to start happening to the concentration of glucose inside that cell? Increase, decrease, no change. Good, good. And don't worry, we're going to write all this down. So just follow. No, let's see. Yes. Where do you need me to go back to? I don't mind going back, but I want you guys to know that I am going to be writing all this down. Right now, we're just trying to get you thinking to the list of glutes. Okay, sure. This is also in the class recording for anybody, everybody that, you know, has trouble keeping up with note taking. You're always welcome to go into that Blackboard recording. Just fast forward to where you need to go, press pause, and then you'll be good to go. Do you have what you need, Litzy? Awesome. All right, so let's go back here. Glucose has entered the cell, therefore the concentration of glucose is increasing inside of the cell. And what do we need glucose for? What do cells make with glucose? Hooah! What's glucose good for? Energy. What is that specific form of energy, Melissa? It is ATP. True story? So just keep working with me. Again, we're going to write all this down in a minute. You don't need to be writing anything down right now. Just everybody should be writing in chat. What's glucose good for? Cellular respiration. Glucose plus oxygen plus ADP and inorganic phosphates makes ATP. So the more glucose that's inside of our cells, the more glucose that's inside of our cells, CO2 plus water. Heat is a byproduct of ATP being burned. So make sure water is there, Tariq, not heat. Yeah, not heat, water. It's got to be H2O. It's really important. That's a metabolic waste. Heat is just a byproduct. Just because, you know, ATP gets burned for work. So that's just a byproduct. But cool, awesome, perfect. Now, there's the link. As glucose levels increase, ATP levels will increase. And these beta cells, they are going to use the ATP for lots of different functions. Something that's easily forgotten in translation is that ATP is a chemical. It's a chemical. And if you recall back to AMP1, I hate doing this to you guys. You guys remember what you learned many months ago. So that's why I'll review it as well. Is that there are different types of channels. So let's do this on my scratch paper. Channels. There are just open leak channels. They're leak channels. They're open all the time. They're called leak channels. They just allow ions to slowly leak over time. Sodium leak channels, potassium leak channels, there are calcium leak channels, chloride leak channels. There are lots of different types of leak channels. Okay, they're just constantly allowing ions to move across the cell membrane. And they're slow. That's why they're called leak. Drip, 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 drip. We also have gated channels, though. And gated channels, there are more of, but they're normally closed. True story? If we have a channel, it's crossing that cell membrane. This one here has a gate in it, and as long as that gate is closed, can anything go through that channel? Yes or no? Nah, of course not. Of course not. Now, the one type of gated channel we've already kind of reviewed is a voltage channel, which tells you what its stimulus is, voltage. So as the membrane potential changes, the stimulus to open up the gate. What is the stimulus for a voltage gated channel? Voltage. 2, chemically gated channels. I'm going to say CG. CG, which is a ligand. They're the exact same thing. A chemical is a ligand, however you learn to pronounce it. So a chemical is a ligand. Chemically gated channel. So chemicals, this would be something like acetylcholine. Remember how it bound to the nicotinic receptors, opened up a channel, sodium rushed in faster than potassium left, and therefore we changed something. Not all neurotransmitters, but Yeah, definitely neurotransmitters tend to be more chemically gated neurotransmitters. The last one are mechanically gated channels, meaning a physical change like osmosis causing a cell to swell would cause a gate to stretch. And as that gate stretches, as it's getting pulled on, it's going to activate due to the change in mechanics. Does that make sense? So these are the major channels in your body. In this particular case, we've already talked about a specific type of voltage-gated channel. Voltage-gated calcium channel. So what does that tell you? When a voltage-gated calcium channel opens, calcium can move through it. Cool? Or what if I had a gated potassium channel? Then when that gate opened or closed, it doesn't, this chemically gated channel specifically allows potassium to move through it. All right, you guys good on that part of the review? God, we're constantly reviewing. I'm so sorry, but it's better than me just saying, you should know this, do it yourself. Yes, what's up, Heather? I just can't bring myself to do the, you should know this. Yeah, I have such better results later in the semester when I do this now. An example of a mechanically gated channel, ones that you haven't really learned about yet, they're called baroreceptors. Baroreceptors detect pressure. So we'll get to mechanically gated channels, but they detect changes in pressure, like baroreceptors found in your blood vessels. So as as blood pressure increases, it's going to push on these mechanically gated channel, change the ion penetration, change the depolarization rate, and start signals to the brain. But yeah, it's one you guys haven't I mean, it's one you're taught about in A&P1, but we haven't really utilized it yet. There's osmotic receptors in your brain that detect whether or not a cell is shrinking or swelling due to the osmotic potential of your bloodstream. So yeah, there's some actually mechanically gated channels. You have learned some. Dummy. Hair cells in your ear are mechanically gated channels. So those cells have the tip links at the very tip, right? And as the current moves, the liquid current in your ear, as it moves past those hair cells, it moves them towards the kinocilium. You guys remember that? Those are considered mechanically gated because it's a physical change in their conformation that either opens or closes channels. Yes, no, maybe so? Shit, that's out of context, but you guys are like, Dr. H, nobody ever taught me that. Sorry, I teach my students about it. Do you guys remember those hair cells? Am I down? Am I lagged? Are we lagged? Are you lagged? Okay, whatever. It's not important for the context of this story. Now, let me tell you some complications in the human body on this stuff. There's a couple of things, more review things to understand. One is that gates don't always start closed. Sometimes gates are actually open. And as long as they're open, things can move across them. And when a chemical or a ligand binds to it, that is what closes the activation energy required to close the gate is the chemical. Sometimes they start open and the chemical will close it. How crazy is that? Welcome to the body. Nothing's ever simple. These are called sensitive, chemically sensitive channels. Okay, these are called chemically gated sensitive channels. The chemical is going to differ. You guys are just about to learn about, the chemical is ATP. So these channels are called ATP sensitive channels. But let's learn what specific ion can move through them, and it's potassium. So there's something out there called an ATP-sensitive potassium channel. Gulp. ATP-sensitive potassium channel. So terminology tells us, what is the ligand? What is the chemical that is going to affect this channel? I know some of you guys are still writing down your notes, so if that's you, don't worry about chat. The chemical that is going to alter this channel is ATP. What ion is going to be altered due to this channel either closed? Potassium. Good. All right. Last review, I swear, because I don't have time to review all of this all the time. Last review is, let's take a cell. And let's remember some terminology. One is a word that we learned already earlier this semester. Polar means to separate. What about potential? This is a word you guys probably remember in A&P1, but probably were never taught what it means. I don't know if that's true or not. Potential doesn't mean high to low, and it doesn't mean stored. You guys are thinking of the potential energy, but that's not what it means in physics. You guys learn about graded potentials and action potentials. You learned about the EPSPs, so excitatory postsynaptic potentials. You guys talked about end plate potentials. So you guys learned about all sorts of potentials. So what is a potential? You learned about membrane potentials too, right? No. Potential in physics means voltage. How bizarre is that? Potential is about voltage. And voltage is electricity. But it's not just any electricity. More review. So with electricity, there are electricity. There are three major words that to live by. One is voltage, two is current, and three is resistance. Viva la resistance. You guys heard these terms before with electricity? Specific voltage battery, for instance, right? Currents, resistance. So what do these things mean? What do these things mean? Okay, voltage is potential, by the way, so they're kind of the same thing. Difference in charge is voltage. Wonderful. So there's actually a visual that helps you understand all the perfect, Tariq. You got it. Current is flow. There's a visual that will help you guys understand these. And that visual is what I've already been drawing multiple times. I have a cell membrane. I have a cell membrane. And I have a gated channel. I have a gated channel that's closed. So I have a cell membrane. This is a phospholipid bilayer. And what do we know about phospholipid bilayers? Can charged things just move through them? Yes or no? Nah, no, not a chance, right? What do they need to move through that cell membrane? They need help. So that's what those channels are there for. So this would be called a resistor. Do you see how it would be resisting the movement of charge? Yes, no, maybe so? It's resisting the movement of charge. All right, next big part of the story is there's a really important transporter in the cell membrane. It's found in every cell membrane in the human body. It uses more ATP than the rest of the body uses combined. It is the most important pump, the most important transporter that you have to know about, you have to know about, you have to know about. So what transporter am I talking about? I'm talking about the sodium-potassium pump. This uses more ATP than everything else in the body combined. Okay, the sodium-potassium pump. Really important pump. You guys must know it. You must know it. You must know it. And the way this pump works, two ways to learn it. One, just gross memorization. Two, a slight variation of gross memorization. The way I like to learn it is, what do you guys know about sodium? Where is sodium normally high? Outside the cell or inside the cell? If I'm drawing my cell right here, God, we got this. Sodium is normally high outside the cell. Now, what do we know about active transporters? Are they moving things from high to low or low to high? Oh, low to high. So if by the way, this is always ICF for me. I always draw ICF on the bottom and ECF on the top. But if I have a sodium potassium ATP pump and it's always moving from low to high, where is sodium always high? Outside the cell. This pump is always moving sodium out. Does that make sense in terms of the logic to how you can learn it? There's an ATP always moving things from low to high. Well, sodium's always high outside the cell. Boom. That's because the sodium potassium ATP. Yep, 3 out, 2 in. You got it. So now what about potassium? Where's potassium normally high? Inside the cell. So potassium normally high inside the cell. So what do we know about pumps? They're moving things from lows over here, to high over here. So now we got potassium going in. It's 3 sodium out, 2 potassium in. I'll never use that. It's important, of course, because it helps with the overall potential. So as we start to do that, you guys notice how I always write the charge on here? I notice in chat, I don't always write the charge. You just go Na and K. That's technically inaccurate. That charge is important because these are called ions, right? If there was no charge, then potassium, sodium would just move across the cell membrane. But as long as that charge is there, these are less likely to cross the cell membrane. Oh, I'm sorry, Melissa. Well, what was your answer? I'm so sorry. Sometimes I go too fast. I'm kind of running out of time, so that's why I did that. Oh, okay, got it. So charges are actually, these ions are harder to move across the cell membrane than proteins because they're just a single big charge. It's pretty crazy. So this is moving sodium out, and this is moving potassium in. And now we start to get buildup of charges. You see how 3 sodium out, 2 potassium, and we're going to get a whole bunch of positive charges building up along this cell membrane. And they're going to be separated from one another because one's sodium and the other one's potassium. You guys with me on this? How were they able to separate? Because the middle is a resistor. Without a resistor, we would never have this separation of charge. True story? What is this separation of charge called? Voltage. That's what voltage is. Voltage is separation or polarization. It's separation of charges. That is what voltage is. So if you get a 9-volt battery, that means that there are exactly 9 volts of charge separate from the plus side of that battery to the minus side of that battery. What it means. Cool. We got to finish off this diagram though, because we're not done yet. Right now we have equal number of charges on the inside of the cell to the outside of the cell. See how there's 4 charges that I've drawn in arbitrarily outside, 4 charges on the inside. So is there any potential here? There's no difference inside. And that's what potential is going to help us with. There's no potential. +4 outside, +4 inside. Okay. That's not great. So the last part of this story has to do with leak channels. What if we were to throw in a potassium leak channel? This will come back and play a big role in what you guys are about ready to learn. Don't worry. Potassium leak channels. So where is potassium higher? Inside the cell or outside the cell? Now, potassium, Tariq, where is potassium higher? Inside or outside? Yep, so it's inside. So now potassium, as long as I have a leak channel for it, will leak out of that cell. Does that make sense to everybody? All right. Last bit of the review, I swear. I know I've said that, what, 5 times now? I swear this is it. Is we want to draw a graph. I'm not going to go crazy on the labeling or anything because we just need to get to a point. But this is that action potential graph you guys learned about in A1. But most AMP1 professors just say, here's a graph, learn it. I'm not that type of professor, sorry. So I'm going to teach you guys how this thing is created. Membrane potential. So if we know it's potential, we know that it has to do with voltage. Voltage in the body is very small, so this is in millivolts. Do you guys kind of remember that, this graph? I'm sure you drew it enough. You probably are like, yeah, Dr. H, I remember it. I don't want to remember it, but I do. The way that we can measure membrane potential is take a cell. This is done in lab situations underneath a microscope. You look at a single cell. You take what's called a microcapillary. So you take a glass pipette and you stretch the tip out until the tip of that pipette is stupidly small. Underneath the microscope, we push the tip of that pipette through the cell membrane. And we kind of hold it right on the inside of that cell membrane. And we can measure the number of charges inside of the cell using this pipette. So over on this side, we're going to have a wire that moves to a voltmeter, a box, that tells us how many charges are inside of this cell. But we also have another wire coming in this box that goes out into the ECF, so into the fluid that we're housing this particular cell. And so it's going to measure the number of charges outside of the cell. You guys with me so far? Basically, we just have 2 wires. One's measuring the number of charges inside, and the other one's measuring the charges outside. No, you don't need to know this for the test. This is kind of just a review. It helps you understand these diagrams a lot more. And if the number of charges inside of the cell are exactly equal to the number of charges outside of the cell, how many volts are we going to have? Or how many millivolts are we going to have? 0. Does that make sense to everybody? If they're equal on either side, it's 0. There's no difference between the 2 sides. Yes? No? The last little bit here is that with the voltmeter, we always compare ICF to ECF. We're never comparing ECF to the ICF. We're only comparing ICF to ECF. What does that mean? Is that as the voltage, as the number of charges changes from inside to outside, we're always going to say what's happening on the inside of the cell relative to the outside of the cell. Let's go back to our picture. What do I mean by this? If more plus charges are outside of the cell than inside of the cell, what's going to happen to this graph? Are we going to become more positive, or are we going to become more negative? If there are more charges outside of the cell than the inside of the cell. Remember, we're always comparing the inside relative to, hold on. Comparing the inside, you're wrong by the way, but we're comparing the inside to the outside. So just let's continue with this. If the outside becomes more positive, then the inside is relatively more negative or more positive. You guys are not wrong. Just Alyssa, Tariq, just trying to get everybody to see this. Let me go this route. Potassium is leaking out of the cell. And as potassium leaks out of the cell, what charge is going with it? A positive charge or a negative charge? So as the positive charges are leaking to the cell, what's happening to the inside of the cell relative to the outside of the cell? Is it becoming more positive inside, or is it becoming more negative inside? Does that make more sense? Did that question make more sense to people? Okay, cool. It's the same idea. If the outside of the cell has more positive charges, then the inside is negative relative to the exact same idea, but in this one we just added the step of ions leaking out. Okay, let's tie this all together. Trust me, this is helping for the entire semester. From here on out, I kind of assume that you're going to know this, so make sure you understand this, please. Potassium leaks out of the cell, but what if the charges are exactly the same on either side? Then the potential would be 0. Well, the potential in your cell is not 0, because if it was, you'd be dead. So as potassium leaks out, the inside of the cell becomes more negative. Who remembers what the resting membrane potential was for most neurons and skeletal muscles? What's the resting membrane normally? Kind of run out of room here, but it's negative 70 millivolts. Man, that came out gross. I'll draw it right here. Negative 70 millivolts. Negative 70, not positive 70, but negative 70. And Jen, good job. Negative 75 is pretty darn close. It's good enough. We'll come back to threshold. Threshold's important, but we got to come back to that. So how do we get to the inside of the cell being more negative? Check it out. As potassium leaks out, positive charges leave, and the inside of the cell becomes more negative. And what if I told you that the cells had a boatload of potassium leak channels? The more potassium leak channels, the more potassium leaks out. You guys with me? And as all this potassium leaks out, what's going to happen to the inside of the cell? Does it become more positive, or does it become more negative? Well, we've already answered this. As that potassium leaks out, it becomes more negative, more negative, more negative, more negative, more negative. And if there was nothing but potassium leak channels in your cell would actually have a cell membrane potential, a resting membrane potential of negative 90 millivolts. I'll repeat that. If there was nothing but potassium leak channels in your cell membrane, then your membrane potential would be negative 90 millivolts. But it's not negative 90 millivolts in most cells, it's about negative 70. So we need to add some positive charges to the inside of the cell to get it to negative 70. Does that make sense? So what we have in place for that are sodium leak channels. There's just not a lot of them. There's only a few sodium leak channels. We're just going to draw in one because there are really not a whole heck of a lot of these things present. If I have a sodium leak channel, sodium's higher outside of the cell, and sodium leaks in, and what charge does it bring in with it? Positive charges. So now as sodium leaks in, we bring that resting membrane back potential up to negative 70, which is where it hangs out at homeostasis. Complex, but really cool if you understand how resting membrane potentials work. Now, the last word here, current, we haven't defined yet. This is the movement of charge across the resistor. I don't know, spell resistors. O-R-E-R, whatever. But now you can see that as we have ions leak, that's current. As ions move from the inside of the cell to the outside of the cell, or from the outside to the inside, that would be considered current. Does that make sense in terms of the terminology, physics? Not that you'd ever need to know that for this. It's how the body runs. Your body is a battery. It runs on physics. Sorry. Chemistry and physics and all this other stuff nobody wants to learn. All right. Last thing I want to do here, using this diagram, chucked one of my lids of my markers, got to get that, is I want to ask you guys a couple of questions. If I were to increase potassium leaking out of the cell, what if I increase the speed of potassium leaking out of the cell? Would the inside of the cell become more positive, or would it become more negative? If I increase the speed that potassium could leak out, it leaks out faster. What's going to happen to the inside of the cell? Become more positive, or does it become more negative? Good, Melissa, too, on the terminology. That's going to be a hyperpolarization effect. Now, is everybody clear on that? Because we got to get back to insulin. And this is the last little bit of what you guys need to understand. What if I had a chemically gated potassium channel that when ATP was in the system, it closes a potassium leak channel? What if I close this potassium leak channel? What's going to happen to the amount of potassium leaking out? Increase, decrease, no change. And therefore, what's going to happen to the amount of potassium that stays inside of the cell? Increase, decrease, no change. You got to remember, these pumps are still working. So the sodium potassium pump's still moving potassium into the cells. So the amount of potassium inside the cell is building up, building up, building up, building up. Everybody with me? And therefore, what would happen to the charge inside of the cell? Does it become more positive, or does it become more negative? And what do we call this? As we have a more positive effect on the inside of that cell, this is called depolarization. And if depolarization reaches a threshold, then a voltage gated channel will open, because we depolarize to the point of a threshold. Is everybody clear? If depolarization hits a threshold, then we will have activation of whatever that channel is. Doesn't always create an action potential, by the way, but it will activate whatever that threshold is. Cool. Whew. Man, that's a big roundabout way to get to what we need to get to, but we need to get to it. And that is the middle of the story, which is the complicated portion of the story. But now you guys have all the pieces of the puzzle required to understand it better. The more ATP that's in the system, the more it closes the ATP-sensitive potassium channel. And if the ATP channel closes, then potassium builds up inside of that cell, causing depolarization. And when it reaches threshold for a voltage-gated channel, it will open up or activate that voltage-gated channel. And in this case, it's a voltage-gated calcium channel. Therefore, calcium influx, calcium driving exocytosis, release of insulin. Crazy, huh? But pretty cool. Did everybody follow that? We're going to draw it all down, and we're going to go through it one more time. But does everybody kind of have the basic gist of the story? If there's an increase in blood glucose level, glucose enters through GLUT2, elevating the intracellular concentrations of glucose, making more ATP. ATP closes the ATP-sensitive potassium channels. No, it's not about charge. That's not what exocytosis is about. Calcium is a secondary messenger. It physically is like a hormone, if you want to think about it like that, but for inside of the cell. Calcium physically binds to the vesicle and helps with its transport. I'll just a quick image just so you can get this. Nope, that part has nothing to do with that part has nothing to do with polarization at all. Calcium physically goes to that vesicle and physically wraps itself all the way around that vesicle. It literally is a big part of the cascade. Don't worry about everything else because it gets cellular physiology gets really confusing really fast. Look at all these different words that you would technically have to learn: CAM kinase and SNAP, and I mean protein kinase C. I mean, yeah, syntax. I mean, there's so much crazy stuff going on in your body that you guys don't need to know about. But those are the sorts of things that pharmacology companies, they're after all those different things that I just showed you because they can create drugs that target each part of the pathway. So, you know, trillionaires because of that. All right. Let's draw this from scratch, and then you guys can let me know if you have any questions. I'm going to take another decent break. Then we're going to learn some about blood. Blood. As blood glucose levels increase, we have a beta cell of islets of Langerhans. And what we have here in the cell membrane is we have GLUT2. What's so cool about GLUT2? It's always found in the cell membrane. It is not insulin dependent like GLUT4. And as long as glucose is in the system, I'll make glucose this pink color. Glucose is in the system, then glucose can move from an area of high to low, and glucose enters this cell. True story? Is everybody good on this? This is called glucose uptake. So that's occurring in the beta cell here. So what's going to start happening to the concentration of glucose inside the cell? Increase, decrease, no change. And the more glucose inside of that cell, what's going to happen to ATP? Increase, decrease, no change. Everybody clear on this so far? Please give me a woot woot. I know I'm losing some of you guys because you're hungry and tired, but I just need some confirmation that you're still alive. Just be like, I'm alive, barely. Now ATP binds to the ATP. Alive, Alyssa says. So now we got this ATP sensitive potassium channel. And it's normally open. It's normally open. Therefore, potassium normally just leaves the cell and it stays hyperpolarized. Sweet, we're good. It's not active as long as potassium's leaving the cell. But in the presence of ATP, when ATP binds to the ATP sensitive potassium channel, it's going to close it. It's closing this thing. And that's pretty darn important because if we close potassium channels, potassium would normally move from inside of the cell out, but now potassium no longer moves out. And so potassium builds up inside of the cell. And that's going to end up causing depolarization. And this depolarizing event is enough energy to activate a voltage-gated channel. Which voltage-gated channel will be activated by this depolarization? I know you guys are writing this down, but can I get somebody? What channel out here are we dealing with? Not sodium. Remember, the next step is going to be exocytosis. So what ion do we know is critical in exocytosis? Calcium. So this depolarizing event is going to be activating a voltage-gated calcium channel. And that voltage-gated calcium channel, once it becomes activated, A, with an arrow up is activation. Nice shorthand way to be able to do your notes pretty quick. Then calcium can move from outside of the cell into the cell. We call this calcium influx. And calcium influx drives exocytosis. Exocytosis of what? Insulin. Boom. Now we have insulin out in our bloodstream. What would happen if we had a pharmacological agent that we gave somebody that blocks the closing of the ATP-sensitive potassium channel? I know, I'm sorry, Melissa, you might have to redraw it. I probably should have drawn mine a little bit bigger too. But again, what would happen if we gave a patient a pharmacological agent that blocks the closing of the ATP-sensitive potassium channel? So this potassium channel stays open. What's going to happen to the release of insulin? Increase or decrease? What's going to happen to the release of insulin? Increase or decrease? You guys got it. Perfect. Because as long as it's open, insulin doesn't exit. What if we start to block the opening of voltage-gated calcium channels? What's going to happen to insulin secretion? Increase or decrease? What if their blood glucose levels aren't high? What if we have hypoglycemia? We have low blood glucose levels. What's going to happen to the secretion of insulin? Increase or decrease? Lovely. And last but not least, what if we had an immune system malfunction that kills the beta cells? What's going to happen to the secretion of insulin? Increase or decrease? And that's called type 1 diabetes. Okay, type 1 diabetes is destruction of insulin, however the hell that happens, whether it's some intracellular pathway or the entire destruction of the beta cell, which is the most common way due to an autoimmune disorder. Your body starts to attack the cells and eats them. It's like, oh, you look yummy, dumb body. Well, that's type 1 diabetes. Type 1 diabetes is a decrease in insulin, not the insulin receptor, but in insulin itself. Do these patients still have the insulin receptor? Yes or no? Do type 1 diabetics still have? Of course they do. The only thing that's affected in these people is the secretion of insulin, because they still have their insulin receptors. That's a good thing, because now we can take a type 1 diabetic, just give them insulin for the rest of their life, change their diet around so they don't have as much glucose, give them some insulin, and we can regulate their blood glucose levels that way. Type 1 is a lot easier to treat. It's very bad if it's left untreated. Can cause severe problems. So, yeah. And then type 2, there's a lot of problems that can occur with type 2 because over time, especially if that patient that you have with type 2 doesn't exercise and doesn't change their diet, then that insulin receptor just continues to desensitize. And as it desensitizes even more, they further and further into the 2 diabetic trap. Change your diet, change your exercise regime, and actually type 2 can be very treatable. Not treatable, but what's the word I'm looking for? Maintainable. Do you guys all feel managed? Yes, thank you. You guys all feel a little bit smarter and a little bit dumber at the same time. It's not my intent, but I know it happens. Physiology is not easy. I'm here to try to help lead you guys through these using flowcharts, using pieces of the puzzle. If there's a piece of the puzzle you don't understand, then text me and I can help you guys understand it better. We can meet up in an office hours and I can walk you guys through some of that stuff. The background helps so much, though. Just understanding how a cell creates a membrane potential really allows this step to become much more simplified, where we block a potassium channel and boom, potassium can't leak out anymore and potassium builds up, therefore depolarization. It's a really powerful knowledge set to have. That's why I spend so much time on that review stuff. I hope everybody appreciates it, and if you don't tell me. It'll break my heart. I just want everybody to be on the same page. I'm not trying to teach one person, I'm trying to teach 24 people. Not everybody has the exact same background. So if I can get you guys all on the same background, I'm a happy camper. Okay, let me minimize that. The rest of this stuff you can look up on your own, right? Glucagon, you should kind of have an idea what glucagon does. There's a flowchart for glucagon. There are other hormones in the body. You guys should know some of these. We've already talked about epi, cortisol, but some of their interactions are in here. There are even more hormones and how they impact blood glucose levels. Can you guys really start to get the point that blood glucose levels are pretty damn critical for your everyday life? Like energy, y'all, energetics, metabolism, big deal, big deal. The disease is associated with changes in metabolism. And I'm going to let you guys, there is a narrated PowerPoint for this lecture, so I'm going to let you guys finish up the rest of those slides. On your own, you guys can reach out and ask me questions on them, but I've spent plenty of time on those. So let's take a break. Everybody deserves a good break. I'd like to just take a break for the rest of the day, but I need to cover more of this material. And what we're going to cover is blood. Where is my blood? But yeah, don't worry about that right now. You guys go take a break. Come back at 25 after. Come back at 25 after. Get some food. That's a decent chunk of time. Get some food. Get some water. Rehydrate. Okay, I have a way to get us out of here pretty quick. Because I know you guys are tired and your brains are starting to not follow me quite as well. They hurt. The brains hurt. All of my brains hurt. So, good news. I'd forgotten I had this, so that's why this is good news. Is that actually I have the entire lab already explained online for you. So, there is a 20-minute explanation of the blood portion of the lab. Now, I'm going to show you exactly what I mean by what I have as an explanation. And then there's also an explanation for the blood typing portion of the lab. So I hope at least one person per group is paying attention right now. Do I have at least one person per group, like fully focused, so we can get the hell out of here? Awesome. You guys are rock stars. And by the way, don't forget, if you have any problems with any of these, you just let me know and we'll make sure that you guys learn this material. So I'm not trying to cop out. I'm just trying to give you guys a break and study this on your own time in the next day. How this all works is that when I give a Blackboard explanation, what I'm actually going into is I'm going into the lab itself. So you guys all have access to the lab. This is not anatomy, so this would be considered physiology. So today's lab is a blood and hematology physiology lab. There is a small portion of this that is also anatomy. So what does that tell you? If you recall from syllabus day, if I have a physiology portion, then there will be a lab report that will be due. Yes, no, maybe so? Just keep paying attention. One lab report per group. Everybody will be receiving the same grade. This is not extra credit. This counts towards the major portion, or a large, this counts towards your grade in the class, not extra credit. One lab report per group. You don't need to have every member of the group submit this. One member per group. Is that clear? I'll be teaching you how to do it in just a second. Now, when you guys click on this right here, the below is a 20-minute explanation for the blood portion of the lab. You're going to have a link. You just click on that. That'll bring up the Collaborate video that I made for this. This was done outside of class. I just used my office hours, and I did a recording for this. You could play, and it's going to bring up my obnoxious voice. So sorry about my voice. And it's going to bring up this exact same sheet of paper that you see right here. Hematology lab, first page is the blood and hematology. You'll see that's the exact same thing that we have here. True story? So what the entire spiel is it walks you through what are today's lab objectives? What should you know coming in? What do you need to know? And then what is the experiment going to be? Which you guys aren't doing the actual experiment, but you still need to be able to understand the experiment, which is blood typing. So this spiel here is going to walk you through exactly what's going on with the objectives. And then what I do is I take you to the lecture. In this spiel, I'll take you to the lecture and I'll say, this information in the lecture, and I'll tell you exactly what that information is, I got to mute myself here. Yeah, 1 second, Melissa. We'll get to the due date in just a second. But yes, it is tomorrow. But anyway, so then this spiel here walks you through the lecture material that you need to know in order to be able to go through this lab. Okay, so this lab handout, you need to know everything that's in this lab handout. But my spiel tells you exactly what you need to know and how you need to know it. Cool? So far, cool? Everybody okay? You're going to watch these. Every single person should watch the spiel on their own time. Yes, no, maybe so? So what this does too is it goes into white blood cells. So white blood cells, red blood cells, and thrombocytes are the three major types of blood cells that you guys need to know about. Well, cells, there are 5 different types of white blood cells, and I walk you through exactly what they are, exactly how to identify them under histology, and what their functions are. So I walk you through all of that. In addition, I give you possible lab practical questions that I can ask, hint, hint, and therefore how I would apply information about, say, for instance, eosinophils and their parasitic helpfulness in a lab practical question. So it'll help you with that, okay? So please go through all of that. I'll walk you through all of the classifications, all of these different guys. And the idea is, of course, basically to answer lab report questions for you. Now, speaking of lab report, everybody, let me go here and go back to what you already have available to you. Everybody also has the lab report available. Do you guys see it right here? Lab 3, instructions for hematology lab report. This is a fillable form, so this is just a doc, a Word doc. You open it up, and now you guys have a fillable form that you can work on as a group, and you need to answer each one of these questions, as a group. And you got this blank page. You are not turning this in for a grade, though. You're just filling it out. So can you write that down for me? The lab report that's fillable that you can get on Blackboard is not turned in for a grade. This is one that you work on together as a group, and you find the answers to everything. So everybody have that written down? This one is not turned in for a grade. Okay, cool. So how do you guys get your grade? You're going to go in, by the way, so I have another one of the recordings for blood typing. You need to watch this one to understand how blood typing works. There's a bunch of questions in your lab report that require your guys' understanding of blood typing, but this will walk you through everything. And I go to my overhand cam and I, teach you guys exactly what's going on with antibodies and antigens, and it's actually I'm pretty impressed with how well that the presentation turned out. So it literally walks you through, if a person has type A, what does that mean? If they have type AB, what does that mean? What are, these antigens and antibodies in the body doing, and why are they so dangerous? Why do they kill patients? And then I go through and I literally answer your lab report questions for you. So watch this video. I'm going to answer your questions that you're going to get graded on for you. All right, so how do you guys get your grade? Do you guys see this one here with the cross or the X and the check mark? Everybody see this tab here? This is the quiz. So you'll click on this and you hit begin. These right here are the answers to the fillable form, which is right here. So you'll notice they follow option 1 blood type based on the results, what antigens are present, what antibodies are present. So now we go back to what you guys clicked on over here, and the quiz says, what's the blood type for person 1? What antibodies are present? What's their hematocrit? You guys see that it just answers the questions that you already should have filled out. Yes, no, maybe so? So literally that's what you're doing here, is you're going and you're just having one person per group do this quiz. Did you guys hear that? You get to choose the person in your group. Choose one person in your group to go online and do this lab report. I nominate Ashley. I love it. You're going to choose one person per group. I can't emphasize this enough. One person per group does this lab report. Then that same person, it's very helpful when it's that same person. I know this is weird, but this is the only way Blackboard allows me to get group grades. I hate it, but it is what it is. So just keep following along. That one person that submits the lab report by doing the quiz now goes to the assignment, which is just below it. And the instructions are right here. So if you have any questions, I literally write them out step by step. You're going to click on this assignment tab, and just like you did for the extra credit, you're going to hit write submission, and you're going to tell me, blah, 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 Ashley Grimm completed the quiz, the lab report. Is that clear? Then you're going to say, these group members helped. And you're going to give me that list of the group members that helped, or just tell me the person that didn't help. Hopefully everybody helps. Then all you have to do is hit submit. You don't need to add anything, no local files, no nothing. And then I'll know which group member to go and grade their quiz. Does that make sense? Kind of? Awesome. If you don't write this, if you don't tell me who took the quiz, exactly, Alyssa, that's done under the assignment, exactly. If you don't tell me who did the quiz, I don't know whose quiz to grade. And if you don't fill in this assignment, then your group gets a 0. If you don't do this simple step right here, your group gets a 0 for the assignment, and that's kind of crappy, right? I will always be lenient at the beginning of the semester if people forget or don't know how to do these things. But the instructions are right here, and you can always text me. So there's really not a huge amount of excuses for not getting it done. Once you type this, you hit submit, and then what happens with me is I can actually go to the Grade Center and I can find your assignments, and I will be able to view your submission. And then I'll go back and I'll be able to find your quiz that you took, and I can grade that personally by hand. I grade everything by hand. And then I will go back and give your entire group the grade that you earned. Does that make sense to everybody? I know it didn't make sense to me at first, but it does exist, I promise. It's the only way. I actually called Blackboard support, and they're like, yeah, sorry, it's the only way that it can be done. They spent 2 trying to research if there was another way that it can be done, and there's not with the version we have. So let me repeat this just one last time, more succinct. You have a PDF file that tells you all the lab objectives. You have a fillable lab report form that you guys work on together as a group. You have a Blackboard recording that describes blood, just the general functions of blood, red blood cells, thrombocytes, which are platelets, they're your clotting ones, and white blood cells, which are part of your immune system. So this one here describes all of that. The video down below describes blood typing, which a large portion of your lab report grade will be on blood typing, and a large portion of your lab practical will be on it as well. So everybody needs to understand this, not just the person filling out the lab report. After your group has finished this, you will have one person per group fill out this, the hematology lab report. That is check mark cross X. And then that same person, because it's easier that way, goes down to where we got the ruler, which is the assignment. And that person says, I submitted this name, and this is the group members that helped or didn't help. Then you click it. Everybody clear on those steps? The rest of the semester will all be exactly the same. So if you guys can do it right this first time, great. So one more thing is that there is histology in this as well. There's only 7 things you need to identify. It's very, very, very limited amount of information, and it's all explained right here in this collaborate, okay? How to identify the different types of white blood cells. You will need to be able to do that for the lab practical. But as such, guess what you guys have? If there's anatomy, because histology is anatomy, what else do you guys have? Remember endocrine anatomy, everything like that. What do you always have for anatomy that you can turn in? No, I'm not going interactive. Work with me though. You're going to have an extra credit. So in addition to your lab report, which is 10 points for your grade, you'll also be turning in a very, very short study guide. 7 slides is all it needs to be. Okay? And that those 7 slides are going to go through the histology of the blood, which I explain in all of my little videos here. So if you go into this video, it literally walks you through the histology of blood. And you guys can just put together a study guide. Yes, Alyssa, 1 second, please, 1 second. You guys can put together a study guide, click on lab group study guides. Now you got study guide for blood anatomy that's available. This is 3 points extra credit. So this is 1/3 of your lab report of extra credit. 7 slides should be really, really easy. Where can you guys find pictures of hematology? Do you guys remember this website that I gave you? Slidebox that I shared with you. I didn't give it to you. Well, you can go in here and you got yourself blood. And it explains plasma, red cells, white blood cells, granulocytes, agranulocytes. Everything that's in my video is here. And you could just go into the blood smear for blood cells, go red blood cells, and you can click on that, go down here, scroll through. You want to find platelets, well, it'll zoom in on these tiny little purple dots. Those are platelets. Go in here, find a neutrophil. Well, there they are with multi-lobed granular. It's all here for you in this slide box. So now you just take a screenshot of this, label it for your extra credit. Easy peasy lemon squeezy, 3 points extra credit potential. Eosinophil looks like a sunburned dude with sunglasses, upside down, but still, you get the point. Sunburned dude with sunglasses and kind of looks more like an alien. Sunburn. Go through my little presentation and it'll make more sense. Basophil, tons of dots. Specific landmarks, that'll help you. Little fried egg. So does everybody have an understanding of what they need to do? Please, you know you can always contact me. So if you're stressing out at all, just walk away from your computer, take a deep breath, and contact me when you're ready to go through some answers. Okay? You guys are done, though, and I'm kind of done, too. These are long days, and we got so many days a week together to get through this. All of this is due tomorrow at midnight, so that's the last of it. Why is it due tomorrow at midnight rather than Monday? Because this weekend is your exam and your lab practical. So you don't want to be turning in, well, maybe you do, but you don't want to be dealing with your lab report after the exam and lab practical because the lab practical is over the lab material. So you need to have it done before the lab practical. So it's all going really fast for you. And that's summer session is a test of stamina, endurance, self-motivation. I'm here to try to help you. Please don't cry too much. I wish I can give you guys all hugs when it gets easy. But are there any questions? If not, I'll let you guys go and ask questions via text when you have them, because you guys have been really good about that. So proud of y'all. Are there any questions? Yeah, unlimited, dude. I want you guys to learn. I'm not here to try to harass you guys. Just unlimited. Due date is tomorrow at midnight. Yep, Thursday at midnight. Thursday. I want you guys to learn, Don't go. I know, Tariq, you can take advantage of that if you wanted to, and I hope you guys aren't that patient. That student that goes in and like clicks A and finds out whether that's correct, clicks B and finds. I don't appreciate that very much, but if it happens and it happens, just learn, because on a lab practical you can't do that. So make sure you're learning as you go. All right, again, I'll let you guys go. Please text me when you have questions. Make sure you text me when you have questions. All right. You guys rock. I want you guys to know how proud I am of you guys already, and you should be proud of yourselves. Stick with it. You got this. Peace.